So good morning everyone. Today's plan is already mentioned here. So yesterday we have basically a very exciting overview of the course, and I think we have covered both cybersecurity cyberspace as well as machine learning space. So today Professor Mishra will cover in the first half the hardware acceleration of explainable AI. How do you implement these things in hardware, right? So those part, and in second half mostly on the malicious softwares, malware, antivirus, and then malware detection using explainable AI, right? So it will be another exciting day to hear. I just want to say one thing. So when you ask question, use the mic in the row, so then the question will also get recorded. Okay. So we try to use this particular recording for future usage, right? So if you ask a question, that should be valid questions, and that would be discussed in the course, right? And it will be recorded. So please use the mic in every row. There is a mic. You can just take it to you and talk on the mic. Okay. So that will help. Okay. So thank you. About this.
Good morning everyone. Let's welcome to the second day. So today our focus is on talking about explainable AI, but one of the important aspect of explainable AI is that because it's trying to explain something, it has a lot of material in it, and if somebody wants to use it, it's going to take a lot of computing resources. So most of the systems, whether you think of car or medical equipment, they have to make real time decisions. Explainability is wonderful, but they should be able to finish in a real time as fast as possible. So if some computation take too long, only way you want to accommodate in real time systems is by making them execute faster. One way you make them faster, you use some hardware based acceleration. So I am going to talk about how do we accelerate explainable AI, but some of the concepts I am going to talk about, I did not want to make an assumption if you already have a background on acceleration or speeding up. How many of you have done any acceleration of anything? Let us say you wrote a program and you tried to make it faster. How many of you have tried it? One obvious way is doing.
I reduced API calls to scripts and also those kind of acceleration using software.
You can reduce the calls, a function call, by replacing the function body. You put the function body there. You can make for loop execution by unrolling the for loop. There are things even in software level, many of you either used or are going to use multi-threading, trying to do parallelism. Parallelism is one way of doing acceleration, but that is you are doing acceleration with the processor itself. So in the first part of my story, I am going to talk about how the processor architecture itself can help you in acceleration. I am not going to introduce multi-threading, that is a software level technique, but in the hardware level, if can I make any changes to my processor itself, so that my programs can be executed faster. Then I will talk about how about dedicated hardware like field programmable gate array, graphics processing unit, tensor processing unit, how do they help us accelerate. So the first part of the discussion is going to focus on how do you accelerate things, and then we will use those technology, or at least depending on the time, one or two of them, how do we then accelerate explainable AI, what does it mean. So let us start with the architecture. If you have taken any courses on computer organization or computer architecture, you kind of then know that there are kind of pipeline, the execution pipeline you think about where your program runs, that basically have some form of, it fetches some instruction, then it decodes the binary instruction, then it executes them, and there might be memory stages, or may or may not, or execute might cover that, then you write back to a register file, And how does this connect to the big picture? Remember when you wrote a, let us say a C or Java program that get compiled in a compiler, and that compiled code is actually bunch of zeros and ones, that binary, those binary and data, whatever that or assembly program, whichever way you look at it, that gets executed through this processor. That is the key idea. Now, how do we speed it up, this execution? I am zooming into this execute part. So, that zoom, I am zooming, and this idea is not new. This is from 1960s in IBM, the vector processing, and when I was doing my undergrad, we had to learn a language called Fortran. Fortran, COBOL and all these languages. How many have heard any of these languages? Fortran. What does Fortran stands for?
Yeah, I usually heard this term. I don't know.
What does it stands for? The name, where did it came from? Formula translation. So, this Fortran or any of those, it has lot of this nature addition, A equal to B plus, a lot of computation. Only difference is you might say, oh, that is I write program like that. No, you do not, because these variables are vectors, arrays. So, this could be an array of 100, this would be a B of 100, and in this interest of space C is 100. This is 100 elements it is trying to add. So, if you are trying to add 100 variables of 100 elements, can we make architecture faster? So, then IBM solution was, how about instead of having one register which is storing one variable of 32 bit, can I store multiple of them in the same register, so that in a single addition call I can add multiple of them. It would be nice if this register was 32 multiplied by 100, but that is not how it is. It is typically some multiple of 32, but not 100 or 1000. Anybody knows why not 100? First of all, binary power of 2, that is interesting. Second of all, in your program, if your array size is 100 or 15 or 13 or 11 or 19, processor designer cannot design for that, right? They will design for something, you have to wrap it around. If this one is a multiple of, let us say, a multiple of 32, if you are doing 100, so then you have to do one call that will cover 32, you have to do another call that will cover another 32, you have to do another call that would cover 32, and then that covers your 96 plus the last call you will cover 4 of addition of 4 of them. So, basically last call you are going to waste, although you have 32 locations, only 4 locations will have valid values, all other locations will have bunch of zeros, nobody will care them, right. But that is the idea, that instead of making a for loop iterating 100 times and you are adding each time one element, here in a call of 4 I am able to add them. That is the idea, and because you have less number of instruction, less read after write hazard, write after write hazard, branch prediction, all those goes down, that gives you the speed up. Any question on this basic idea, that instead of adding 2 elements at a time, we can add more elements at a time, and this is only useful when your program has lot of vector operation. If your program has scalar operations, then even if you have architecture like this, it is not going to help you. You are just wasting your resources. If you have 32 locations in this register, only one of the location will have value, everything has zeros and nobody cares, that is not a good idea. Now, I want to show you the code. What I am trying to do is I am trying to compute y equal to a times x plus y. A is a scalar value, think of 5, 10, some number, x and y are vector arrays, and this is in MIPS code. So, it is not important if whether you have done the assembly. So, it is basically you are loading the value of a into a register, then you are adding, then you basically loading the value of x, you are multiplying with y. So, this particular one is done with a times x, and then you load, then you add, then you store, add this load is you are loading the location y, and then when you add, this add is a times x plus y, when you store, you are storing into y, and then these are basically adjustment of the array pointer. So, for example, here is the X array and it has all these elements, here is the Y array, all these elements. So, the first pointer points to the first location, this pointer points to this location, this pointer points to this location, all these are basically you are incrementing by 8 bytes, because it is a double operation on the double, it is all of them are 64 bits, that is like 8 bytes. And so, 8 bytes you increment, then you do the loop bound, you take care of it, and if its loop is not 0 you go back. So, you are doing this for 100 times, and there are, because this is if you count 1, 2, 3, 4, 5, 6, 7, 8 and around that kind of stuff, you multiply by 100, you are looking at about 600 instruction. If you do in a normal way, normal processor, each register is 32 bit or 64 bit, that is how you compute, it is going to do 600 instruction. If you have the architecture I showed in a previous slide, then in a single load you get the all of the variable x. In a single multiply, you multiply all elements of x. Think of, you have values 5, 10, 20, whatever values. If you are multiplying by a, let us say a is equal to 3, you are multiplying everybody by 3 in the same shot. So, this become 15, this become 30, this becomes 60 and so on. In a single instruction of multiply, you are multiplying all elements of that array by the scalar value of a. That multiplication is done, then you load y, you get the whole array in a single shot, and then you add, you are done with that. And so, basically now you are looking at about 6 instructions, 6 versus 600, that is the speed up of 100 times. Any questions? Use the microphone please. Yes please.
Sir, so in these kind of architectures a larger ALU is required?
ALU has to be larger, thank you, and the register also has to be large to accommodate this. And in reality, as you realize, in your program you can define any vector size, but your architecture may not support it. So, that is where there are practical limitations to that, but yes, you need that kind of structure. So, the practical limitation I wanted to just show, in a typical architecture you have all these array elements and this one ALU which can add only 2 32-bit numbers at a time. So, if you have 9 locations, you need 9 clock cycle to perform, but if you have 4, unless you have 9 parallel adder, you can't do in a single clock cycle. So, for example, if you have 4, somehow this 9 you have to divide in this manner. So, you need at least 2 clock cycle. So, depending on how many resources you have, that is how it is going to go. Even if your register size is big, if you do not have the ALU of that size, it is not going to work. But that is a practical limitation. For this discussion we are going to ignore, and as you realize there will be practical limitations. In the previous example I talked about 100x speed up, in reality 100x will not happen, that would be determined by how many parallel computing resources you have, and that is fair expectation. If you put 4 employees, you can't expect 100 times speed up. If you put 100 employees, you may not get 100 times speed up, because people are not friendly, they have ego and all that, manager, interdependency, people become sick and all that. So, 100 would be your maximum expectation, same thing here. As you can see, you have 4, but you are not getting 4x speed up, because there would be time when there would be nothing, because when you divide, there would be time when some computation has to be stalled. So, that is about the architectural modification to accommodate vector operations, that is the vector architecture. Now, I want to introduce one more architecture. In 2000 Intel introduced it, and the Intel SIMD extensions. So, the idea is, okay, instead of telling the idea, let me ask you a question. How many of you played or used any data set that deals with audio or video, directly or indirectly? I am expecting all hands, because that is most of the people waste their time on, playing video game and going and browsing through, what is it called, reels or whatever those are. That is all about multimedia data, audio, video. In fact, most of the data, 99% of the data in this world is audio and video. There are few backdated people like Professor Karfa and I who are so backdated, we deal with scientific data. Most of you guys are smart and advanced, you deal with multimedia data, which Dr. Karfa and I think are useless, but you will figure it out in another 20-30 years, how you want to waste your time. But that is not the discussion here. Let us zoom into multimedia data. How do you think multimedia data different from scientific data? Scientific data like these instructions we are doing 32-bit instruction, how is it different? Do you think there is any difference? Let me spell it out for you so that you can answer me directly. So, let us focus on multimedia. There are lot of types of data. Let us focus on two types of data, audio and video. And the type of data we deal with, which I think normal people like me, we deal with 32-bit or 64-bit, let us say integers. That is what we deal with, scientific data. Do you believe audio video data is any different? You can define a variable x and you deal with that, or you think they are different? How many of you think they are same? How many of you think they are different? Why do you believe that is different?
So because the way of representation is different. For an audio file, sir, I am.
But you are defining a variable integer. For the computer, what difference does it make?
Yes, if I with that variable I store an audio file, it will be kind of the same for the.
It is different. It is different. Video data. What are you storing in video data? Let us focus on video. What am I storing? Let us say I am comparing faces, right? Whether in my brain doing or machine learning is doing or a military aircraft trying to find a target to hit a bomb, they have a picture of the place and then they are taking picture real time and then they are comparing. So, pixel by pixel, millions of them at a time. So, each of these pixel, anybody knows what is it represent? Do you guys deal with 99% of the time, waste you time with this and you do not know what you are dealing with? Each pixel, what is it? RGB values, right? Thank you. Now I don't, I am okay that you guys are wasting time, at least you can say. Now let us go to the next time, RGB, what exactly, how many bits representation it is? What does it capture? Intensity, and intensity ranges between 0 to 255. So, each of them further if I divide, it is a intensity which ranges from 0 to 255. How many bits do I need to represent 0 to 255? Then did we decide the 8 is not equal to 32? Now, if you add lot of 8, then it may become any number. Remember, these are millions of pixels, each has RGB multiplied million multiplied by 3 RGB multiplied by 8, that is a lot of them, or even if you focus on each pixel 3 multiplied by 8, that is like 24 bits, it actually has more than RGB values in reality, depth and all that, but each of those element is 8 bit for video at the smallest level of granularity, and R value has nothing to do with G value, they are independent of each other, they are not even cousin, they are not cousin brother, cousin sister, right. So, when you are comparing two images to see it is a perfect fit, you are really comparing R value of this image with the R value of that image. So, you are dealing with 8-bit data. If you are dealing with 8-bit data, if this is a 64-bit register, if 8-bit would be sitting somewhere right here, all of the values would be 0. Is that a great idea? That is a bad idea. You are wasting the resource. And Intel in 2000 realized that people are for any computation, any program people write, they are going to deal with lot of audio, video, multimedia data. So, we need some mechanism where we can do, we do not waste this kind of resources. So, they want to take advantage of those resources and they came up with this idea, can we put multiple of those words. So, for this one is for the audio example, so I will come to that. But I want to tell you the idea that I should be able to capture 8 data here, 8 cross 8, 8 data from 8 different pixels in the same register, 8 data from 8 different pixels for another register. In memory each of them stored as 8 bits. So, there needs packing instruction, unpacking, all that I am not discussing, but in a single load you get the data, but this data has nothing to do with this data, which has nothing to do with this. If you add, addition will continue, you will be able to add word 3 of this one with word 3 of that one, that is the idea, right. So, you do better utilization. Now, for audio, I do not want to spend this much of time discussing audio. Can anybody tell me what is the size of the data, audio data?
Depends on sampling size.
Nope. What is the number? I am looking for a number. It is a fixed number in the world and it is determined based on what you said. So, your answer is correct. Sampling frequency is important, but what is that sampling? Actually, it is not sampling, it is the quantization. How many bits used? It is 16 bits. I told you, right, this is for the audio. I gave you the answer. For audio, it is 16. Without spending too much time, why it is 16? Because Nyquist's theorem says that if you represent an audio data with 16 bits, the waveforms that you will be able to capture, that is human audible range. If it is for a dolphin or cat or dog, they might have a slightly higher frequency they could be able to hear, but for human audible it is basically the 2 to the power 16 space is more than enough. Unless you think you are a superhuman, you can hear things from other galaxy, that is a different story. For most of us 16 bits, that is why all audio data in the world is 16 bit. So, that is why in this 64 bit representation you have 4 of them. Just by looking at it, can you tell me what is the speed up here? Because we are talking about acceleration using SIMD architecture. What is the speed up here? Everybody nodding head? 4 times. In this audio example, instead of putting one word and everybody 0 versus putting 4 of them, I am making it 4 times faster, because you are able to do 4 addition in a single shot. Of course, as I said, packing, unpacking, the initial overhead, if you ignore that, how do you load the data in the memory in the first place? So, then it is a 4 times improvement, that is the speed up. Any question? Only thing I did not still tell you, which is this adder. Remember, Intel came up with this idea, these instruction set extensions for multimedia instructions. This adder most of the time would be used for normal operation and once in a while for multimedia instruction. Do you see a different how this dude would have a problem dealing with them? Carry overflow. If all of the data is same, then carry will propagate from each bit to another bit, but because these data are independent, the carry that is coming from here to here, that should not propagate, 0 should propagate, because this word and this word has nothing to do with each other. That is why I will show you a modification. So, this is a 32 bit register, each 16 bit. This is actually Hewlett Packard precision architecture, and if you can see the carry propagation between the stage has this multiplexer, and the selection line, am I doing normal add or half word add? If I am doing normal add, then it is basically going to send 0, and if it is a 0, it is going to select the top line, which is whatever was the carry, it will propagate through. If I am doing half word add, then 0 will propagate through. How many of you have questions? Because if you, I am going to ask you a question now, I am expecting all hands. In this story, how many multiplexer would be needed? You are not supposed to answer. 3 multiplexer would be needed, 1 in this boundary, 1 in this boundary, 1 in this boundary. Then the same adder would be able to be used as a full adder and as a multimedia adder, same architecture. Of course, the assumption is we are doing ripple carry adder. If you do carry look ahead adder, carry save adder, all that design will not be supported here. So, now if you go for the SIMD code, I will not get into the detail, but only thing I wanted to say, SIMD gets you 4 times reduction. This should not be a surprise. I am able to accommodate only 4 data into one register. I am able to add 4 of them at a time. So, that is going to give you 4 times compared to 100 times in vector architecture. Of course, we also discussed there, it is not 100, it depends on how many parallel ALUs you have. Typically, it is 64 ALUs in IBM architecture those days. So, then it is 64. So, through architecture or through today's processor itself, you will be able to get speed up only if your applications are multimedia types. In case of SIMD, if it is of vector, a lot of array operations, array addition, array subtraction, then vector architecture would help. If none of the above, then only help would be multi-threading, but even then compilers should be able to find lot of parallelism in your code. If you wrote a code in such a way, every statement depends on the previous instruction, then multi-threading will not work either, but that is still a possibility. Before you go for any acceleration, you want to think of what can I do with my current processor itself. Any questions? So, this is basically kind of I am going to talk about. So far I talked about how a processor itself would accelerate your application. Now, I am going to talk about how field programmable gate array, a dedicated hardware, is going to help you. Now, in a bigger scale of things, I want to discuss three distinct choices in design. One is the CPU or processor I talked about, one extreme. Then other extreme is ASIC or application specific integrated circuit. FPGA is somewhere in the middle. So, in terms of flexibility, CPU is the most flexible one. Using CPU you can run anything. If you can write a program, you can run anything. Using ASIC, that is not possible. ASIC basically you hard coded design something. If you design an adder all of its life, it is only going to be able to add, that is all it is, nothing else it can do. On the other hand, FPGA is a reconfigurable fabric, which I am going to talk now, which you can do, you can change, but it is not as flexible as CPU. So, from a flexibility index, so this is basically the flexibility side, more flexible. And in terms of efficiency, energy, power, performance, this is the efficiency side, this is the thing. So, processor is least efficient in terms of acceleration, energy efficiency, speed, whichever way you look at it, power. If I want to make it little kind of what do I call silly, this is how example. Let us say I wanted to implement a picture like this. Of course, it does not matter what this picture is. If I want to implement this picture, that is all I wanted to do. I did not do it right, but if this is what I wanted to implement, let us say this is a design of something, then an ASIC will exactly design that. That is your ASIC. Let me write that deep inside. This is ASIC. You exactly design whatever is needed. Now, how the other folks will look with respect to this? Let us choose red. No, it was red. Let us choose purple. If you are talking about FPGA, FPGA probably something like that is probably is FPGA, all of it. So, it can accommodate other structures also inside like multiplication, division, but it is slightly bigger. If all you wanted to do addition for rest of your life, using FPGA you are wasting some resources. The reconfigurability that you provide, that comes with the cost. If you are thinking of CPU, if you really wanted to make close, maybe instead of square, let me take another color. So, instead of square, it is kind of going to be a, so that is probably CPU. It is much more bigger, lot more features, some of them you may not need. So, let us say it has a floating point operations or floating point execution unit, but the thing floating point may be not there even in the program, but you are still paying for it, it is still consuming energy. If you say, oh, I will do shutdown and power management technique, that power management logic also is going to take you some energy. Let us talk about field programmable gate array. And so basically in the previous discussion, as I talked about CPU and its power, now I am going to talk about how reconfigurability is going to give you the benefit. It is a lot of information and text, I will straight go to the reconfigurable. The idea of reconfigurability or field programmable gate array is that you have lot of elements, repetitive elements of computation node, and then some form of communication. And if you go back to your childhood, I do not know whether you played, we played that you have bunch of numbers or bunch of cities, and then you have to, let us say this is Kolkata, this is Chennai, this is Mumbai, and there are all these places, and we have to go from city A to city B, and there are many such connections you have to make without overlapping. Let us say there was a requirement Kolkata to Chennai, and you can choose any path. So, this is computation, you can start from here, one of the middle places, but then you have to choose one of these paths to go to Chennai. Now, let us say from so you go to Chennai, from Mumbai, let us say I need to go to Delhi. So, then you have to choose how do I go from here, and then without touching, maybe this side is not allowed. So, there is no way, or at least if I come this way, there is no way I can jump through or go through any kind of way to connect Delhi, but that is what I want to do. So, this is communication reconfiguration. When some computation going on in any of these computing elements, which I will show in a moment what happens. I am going to show you what is the computation reconfiguration, but communication reconfiguration is also needed, because you are doing lot of computations, but they are related. You have to connect those, or one computation is producing something, another computation is consuming, you have to make that connection. So, communication reconfiguration and computation reconfiguration. So, next 5-10 minutes I will zoom into computation reconfiguration, but I want to ask you, is it clear this communication reconfiguration problem? You have a lot of computation, one of the node will not be able to do, you need lot of nodes, actually you need millions of them, and then somebody is producing something, somebody is consuming something. That is like our childhood game from Calcutta to Delhi, Mumbai to Chennai, all those connections you have to make. And how do you make it without the crisscrossing each other? What does crisscrossing mean? Some data is flowing through zeros and ones, you want to throw some more data on it. In general, it is not a problem. If the size of that bus, let us say is 64 bit, then two sets of data can communicate. If size of the bus is 32, we can still communicate. Anybody knows how? If two people each has a size of 32 bit, wants to use a bus which is also 32 bit, how do you do it?
Simplex mode of computation.
Multiplexing, time multiplexing you do. So, you have still bus, physically think of a bus. In the morning we use it, in the evening maybe IIT students use it. So, as long as that they are not needed exactly same time, it is all right. But what if two computing nodes are producing the data exactly same time and two other nodes needs exactly, then we have a problem. That is why the way you place the computation, that is also a difficult problem in FPGA. So, although I am talking you to FPGA fabric, but to get the speed up, you do not get the speed up if all those things are not done right. Now, most of the things you do not have to worry about, because whichever FPGA you are using, Xilinx or Altera, and it is not a surprise, these companies were flourished before Intel bought Altera and AMD bought Xilinx. And whatever the story is, if you use their tool set, they will take your design, break it down into pieces, map it to these nodes, place them correctly, route them correctly, configure them correctly. Once they are configured, they are going to run almost at the hardware speed. Processor going to the programs that you are going to run, it is still the speed you are going to get millions of instructions per second. Here it would be able to run billions of instructions per second, actually in gigahertz you will be able to run here, because it is hardware, FPGA is a hardware. Now, each of the computation, the configurable logic block, I am going to zoom into the computation reconfiguration. Each of the if you further zoom in, lot of size slices, lot of connectivity. If I log into the slice, only thing I want to show you, how is it magically possible same computation node can do addition right now, subtraction 5 seconds later, does it have all the adder, subtractor, multiplier like ALU? No, that is one way of doing. You have all that thing, you select one of the thing, but FPGA does not work that way. So, to show that, I created a funny story here. This is actually not real, this is actually not how it works in FPGA, but I thought of how do I show it to you. So, truth table, I hope all of you are comfortable. This is a AND gate truth table. You have input x and y and output z, and let me draw an AND gate. So, this is an AND gate and we have x and y and output is z. Look at the truth table if you agree. If it is 1 1, then output is 1, otherwise output is 0. I am trying to implement using multiplexer. So, if you want to implement exactly this magic logic inside this box, x and y is input, z and output, I have to use x and y as the selection logic for the multiplexer, and this output of this truth table, these numbers here is exactly same as this number here. That means, if x and y is let us say 0 1, I want output 0 and it is going to select the second line and output is going to be 0. Convince yourself this will perform AND operation. If you are convinced, all I have to show you, if 5 seconds later, 1 millisecond later I want to perform the OR operation, only thing I have to change, whole structure remains the same. Instead of this truth table, I have to just provide the output of this. I have to replace those values with these values. I will come in a moment how do I do that. I have to just replace those values, that is it. Somehow if I can do that, I reconfigured that computing structure to do OR operation. If I want to do XOR, same story, I just replace that original value with the output of XOR logic. Just convince yourself that this structure is exactly the same, only thing different is this 4 cell memory logic here, those values are different. If I can supply those values, that is my reconfigurability of the computing logic. Again for the disclaimer, this is not how FPGA is implemented. I just wanted to show you how can you use the same logic, same lookup table to do whatever you want. If you are convinced with that, then the big picture is when you write a design in Verilog, VHDL, whatever is your favorite hardware description language, in our case explainable AI logic, I am taking a simple expression, and then once the Xilinx or Altera compiler compiles it, it produces bunch of zeros and ones, we call it a bit stream. Exactly the way when you compile your C or Java program, it produces either Java bytecode or assembly, that you apply assembler, you get the binary. Here the same analogy, you do the FPGA synthesis, you get this, and coincidentally these colors are not random color. These values are for OR operation, these values are for AND operation, these values are for XOR operation, and this is also, these values are also not random. This is exactly the output of those truth table. So, for example, look at 0 1 1 0 for the XOR, and let me go back to that slide. XOR, the truth table output is 0 1 1 0. So, if it is a 2 input, that is the exact truth table output. So, synthesis tool produces exact that, and then when I want to do reconfiguration in the FPGA, remember each of them is a configurable logic block. So, then I have to just map these values 0 1 1 0 for OR operation, this is 0 1 1 1, this one 0 0 0 1 is this one is. So, this is basically doing the XOR, this is doing AND, this is doing OR. Sorry, 0 1 1, oh 0 1, oh, different color would help. So, that is maybe white will help. 0 1 1 0. So, typographic problem. So, basically it is exactly implementing this, only thing remaining is now this communication reconfiguration. In reality this is not how it is done, it goes through these boundary lines, but I just connected it just to show that this will produce something that feeds to the first one, this produce something feed to the someone, and this final output A B C D, yeah, final output is A in this expression, that is basically the final output. And again this needs to be routed through all the way to the primary output. Let me go back few slides just to show you if you. So, the finally let us say whatever the final computation is, that need to be somehow, that should be routed, from that it needs to be routed through one of these pins and final output, that is kind of downloadable. Any questions on FPGA or reconfigurability? So, what is the bottom line? We are going to use this fabric to speed up our computation, to speed up our explainable AI. And there are a lot of work, if you want to pursue this line, there are a lot of work, how do you take AI algorithms. So, I keep talking about explainable AI, but even AI acceleration is also important, people are doing it, and that is also done, most of those acceleration is done through either GPU, which I am going to talk, or TPU or FPGA. So far I talked about how FPGA can speed up the execution. Now, I am going to talk about how graphics processing units can speed up the execution. As the name suggests, graphics processing unit, it is basically designed for graphics, and it all of this started from a company called Nvidia 15-20 years ago. And remember 2000 Intel came with multimedia instruction extension. So, for every add instruction there is a add byte, add half word, add double word, there are so many instructions they came with. What Nvidia realized, if everybody except Dr. Karfa and me, if everybody is dealing with multimedia data, why do we take a computing core that is designed for scientific applications and try to change it to do graphics processing, or why not design something for multimedia processing, and if Dr. Karfa or I want to do scientific computation once in a while, it is okay, because that is least important. If the whole world is interested in multimedia data, let us design something from, what is it called, from ground up, let us design something for purely for multimedia speed up. Now, it is kind of seems silly, explainable AI and all that is kind of scientific computation, how come GPU would be useful, we will discuss that later, but I want you to understand the processor philosophy or vector architecture, you are still building on normal architecture. The Intel the extension also building on normal architecture and trying to change it to accommodate something, but if the one you are trying to accommodate multimedia, if that is 99% of the story of the world, let us design an architecture for multimedia processing. And the Nvidia became multi-trillion-dollar company. One of my PhD students became billionaire, because you join a company right on time and that company has to flourish, become multi-trillion-dollar company, then you become billionaire in no time. He is a chief architect of Nvidia. But the point I am trying to make here is not the money, point I am trying to make here how Nvidia became successful. I want you to understand, they saw the market, even then they were struggling. I knew day to day what is going on, they were struggling, they came up with the architecture or design, they do not know what to do with it. They were giving us money, the professors, what are you working on, bioinformatics, okay, try running this on bioinformatics and see if you can do something. They are giving people money, free GPU set for you to do experiments. So, medical people, bioinformatics people, biology people, science people, maths people, every architecture people, compiler people, everybody getting GPU, they are trying to apply and nobody is seeing any success. And inside there, internally in the company, they were trying to implement something called CUDA programming language. They quickly realized there is no way you can provide all these parallelism, and in fact we were happy, we got used to the idea that I have a GPU of 1024 cores and we are getting 5 to 10 times speed up, we were happy with it. Do you see the funny thing? You are giving me 1024 cores and I am getting 5 to 10 times speed up. That is like you can look at it as a 100 times 10 times speed up, or you can look at it as a 10 times slowdown, 10 times of the resource wastage. So, very quickly Nvidia figured out in couple of years, scientific computing speed up and GPU, that model is not going to work. or in a desktop processor putting some Nvidia GPU, they won't be able to make a lot of money. So, then they came up with this CUDA development environment. Even then this programming was really painful. I will show you a CUDA program. This is how CUDA program, and we were writing by hand. So, if remember that x equal to a plus b, a equal to b plus c, to write that thing you have to write all this stuff. So, it is actually lot more pain than writing normal program, and again Nvidia figured out this CUDA programming is. So, basically instead of compiler finding the threads a equal to b plus c, each of them is a vector. You break it down into how many vector, how many element, and you are saying okay, there are each thread has this. You are basically extracting the thread, writing them yourself. That is not going to work. Then came the ecosystem of Python library and PyTorch that would automatically generate CUDA programs. You won't even know, you don't care. Then it would map and run on the GPU. This whole ecosystem got developed. Then that is basically the boom. So, for you to start a company and become successful, you have to do a lot of stuff. Many years you have to spend. Even the VMIPS example I talked about, the original architecture was MIPS. Even before that, the predecessor of that architecture was DLX, and it was designed by none other than Hennessy and Patterson. Hennessy is the Stanford president, is or was the Stanford president. Patterson from UC Berkeley, those are topmost people. Even they could not convince the community that you going the Intel route, complex instruction is not a great idea. So, if you want to really speed up and low power computation, this is the great idea. What did they do? They took leave of absence from Berkeley and Stanford. They started the company, made it successful, then people got convinced, and eventually they got Turing Award and became Stanford professor. That is a different story. I am just telling you, even this acceleration and speed up story, if you really see the back end story of it, the journey is not pleasant for even for people like Hennessy and Patterson. They had to go through all of these. Of course, end result is wonderful. And then MIPS, related to those of you who are following these days, Intel AMD architecture or ARM Intel AMD, those are the general purpose, and then RISC-V is the kind of community academic open source kind of variant. That is what we are talking about, and I will talk about this also one of the lectures. But this is the CUDA programming. This is what it used to be, but the ecosystem got changed. So, that is why you do not have to learn CUDA programming anymore. But what you have to do is basically, this is one of the old one. This is the Fermi is 2010. This is the these are the internal code name. This is not what you buy, but right now they are selling Blackwell. That is like really expensive. So, I think G-Force or maybe one of those A100, that is $30,000 a piece, $20,000-$30,000. These would be even more expensive per piece. Blackwell, next coming Rubin. So, these are the movement, and I will show one of them. Maybe I will show you Fermi and Pascal, just to show how is it different from the fetch, decode, execute. Where is it giving you the speed up? What is going on? What is the magic? That magic I will spell. But this code name and variation, this should be same as even in the processor world. The 8086, there are many variations, Pentium 5, 6, NetBurst, Intel Core, and I did not list all of them. In the GPU side, the same story. So, I am going to zoom in. Before I zoom in, do you have any question? So, as you can see, there are a lot of parallelism right there. This remember the SIMD, that was the reason I explained you that SIMD architecture, because it still implements that SIMD single instruction multiple data architecture model, and if you zoom into SIMD, it is nothing but an integer and floating point unit. But there is a lot of parallel computation node, and the model is different. Instructions are getting pushed from this way and data is getting pushed this way. This is not the von Neumann architecture that we are used to. In von Neumann architecture, instruction is the boss, data comes to the processor. That is the assumption and idea. Instruction flows through the pipeline, data comes from memory, hard disk, and travels. So, instruction is the master in a master slave architecture, data is the slave, but in a multimedia world 99% of the story is data. So, data is the boss. Why should data come? Instruction should come to the data. So, then before GPU happened, there was a world of memory based computing or computing in memory. Instead of data coming to the instruction, why not instruction goes to the data? Why do not we compute in and around memory itself? But that did not go too far, that still has lot of good applications, that did not go too far. Here data is getting pushed from this side and instructions are getting pushed from this side, and there are lot of parallel load store. There are memory at the SIMD level, there are and so that is one speed up, data and instruction coming through, one speed up. Second is, you have to understand this is actually doing vector architecture. GPU is not good if you have too many if then else, and we are operating on few bits or few bytes and trying to compute some control flow. GPU is not good for that. GPU is good for data level parallelism, lot of data level parallelism, not instruction level parallelism. Few instruction, lot of data. Remember, in vector architecture it was also good for the same thing. You have one addition, but it adding arrays of size 100, 1000, 5000. So, lot of data, few instruction, that is the model, data level parallelism. If your program or the domain, do not throw GPU wherever you feel like, do not do that. It only flourishes when there is a data level parallelism, lot of data, lot of this is another. Second thing is, in normal processor, operating system handles all these task scheduling, moving thing, context switching, all these stuffs are gone. All that scheduling and all that are done right here, thread scheduler, everything is here. Think of operating system, million line code operating system got minimized into few 100,000 lines of code, even then that was converted to hardware, that is not even running in software, that got converted to hardware. And these thread scheduler thread, remember I showed you a CUDA program, let me see how far away. So, each of them is a thread. If you wanted to add 100 elements, so it will create 100 of these, I is so 0 0 0 1 1 1, it will create 100 of this is called thread. One individual element addition in a vector is called a thread, and those threads is going to schedule, is the thread 1 going to be executed here or there, and then also it will make sure the way data is coming, the instruction and data they get closer to each other, so that they do not have to cover long distances through this communication path. So, minimize communication, data and instruction both glues together to the computing node, and as soon as results is done, data get transferred to the node that wants to use it, and they will be placed even nearby as possible. So, some of the ideas of FPGA that also gone in here, the placement logic, some operating system got out of the story completely, and this is basically how it is, the GPU, standalone GPU. But in the real world, people use a heterogeneous architecture, which is you have a CPU or kind of fetch, decode, execute that, and you also have a GPU, and the way it is used, CPU is still assumed as a master, and GPU after fetch, if you like what you want to execute, then it is great. If you do not like, you use the help of GPU and data somehow comes back. It is like a co-processor model, heterogeneous computing model with GPU as a co-processor. Like the way most of the camera application, you have a digital signal processor as a co-processor, JPEG co-processor, GPU as a co-processor. This is mostly in your laptop, desktop story. But when we run all these AI applications, it is pretty much either you are using the GPU in the cloud or GPU in somewhere else. University of Florida has a hypergator thing, that is the largest academic Nvidia donation. We got about initially 75 million, then I do not know how many we got. We got all these high end GPUs, 100 or 1000 of them, and we just run on them. Tons of computing node, tons of GPU, and because the Nvidia vice president is our student, that is why we got everything for free. So, that is basically what Nvidia or GPU story today is. Any questions on the speed up? All I wanted to highlight, why does it give speed up? Yes, please. Microphone, please.
Sir, What's the difference between CPU and SIMD?
CPU and SIMD?
Yes.
Remember we talked about in a multimedia instruction, in video we have 8 bits. So, instead of using whole register to store 8 bit, can I store in a 32-bit register, can I store 4 of 8 bits from 4 different pixels. So, then if I do add, I can operate on 4 fixed pixels at the same time instead of 1 pixel. That is called single instruction multiple data. Single instruction is add, for example, and multiple data is data from, let us say, R value from 4 pixels. That is the SIMD idea that I talked about in a normal processor, which is also Intel, AMD, all processors today come with SIMD support, and GPU, of course, GPU will give SIMD support. Any other questions? Yes, please.
So nowadays they have GPU specific for AI computation on laptops and desktops. So do they have something different from the typical GPUs right now you are discussing on?
Yes. So, answer is yes. So, basically when somebody says it is a GPU for AI, remember in early days we were getting all this free money to explore, that is like GPU with this model. As I go along you will see. So, basically the whole ecosystem, compiler, mapping, Python code, support for PyTorch, and those function compatibility, API call, everything got customized for AI, because people 99.999% of the people are using for GPU for AI only. For AI only. If everybody is using exactly the way I made argument, 99% of the people are doing multimedia computing, nobody is doing scientific computing except backdated people like me. Similarly, even with the GPU space, even in the multimedia space, most of the people are doing AI, either AI training, AI prediction, AI this, AI that, mostly training actually. So, then whole ecosystem, tool set, chain. So, if you think of a change from architecturally, there are few minor changes, it is actually the tool set, whatever that ecosystem, so that you do not have to do too much of stuff. And if you are thinking what do you mean by too much of stuff, I need to take you back to FPGA to kind of show you something. Even today you will face that problem as we speak. In the FPGA space, let us say you mapped a design in here, and then you thought maybe I can optimize the design little bit. Let me map a tiny smaller design, D prime is smaller than D, and you try to measure power and all that stuff, there is no difference. Right? Reduce it to 1 transistor and map it, there is no difference, because unless you take one of the output or all the output and XOR it and connect to the primary output, the synthesis logic will remove everything, realizing you are not using any of these output. So, why would I keep them or map them, they will delete it. It took me time, it seemed silly to me, but that is what everybody does, that is one of the hack we do, so that the synthesis tool does not eliminate it. And then when I talk about electromagnetic based side chain analysis, where you place it in FPGA, controlling it is important. If you do not control it, then you will be putting your probe here and there, you are trying to measure my temperature not in the forehead, but somewhere you are touching your thermostat on that. That is how FPGA thinks, you are touching the thermostat on that door, it is not going to give you a temperature of the body. So, there are all these idiosyncrasies, GPU got rid of all these idiosyncrasies. So, that from a user perspective, you write a Python code, you hit the button, it just gives you the speed up and run. So, now I want to conclude this one, basically the subsequent one Pascal. So, as you can see, the change between, I just want to show you pictorially, the original Fermi in 2010 and Pascal in 2016, lot of parallelism, lot of cache. Now, then in addition to the caches and memory, in between layer also there are a lot of caches. It is just data basically everywhere dominant, and in fact if you zoom in, there are caches also here everywhere, so they have different names, naming conventions. So, grid, cluster, so they have memory grid level, cluster level, block level, SIMD level, every layer they have tons of memory, data parking space, data coming in, data going out, lot of that. And then so this is 64 SIMD. If I zoom in one of those, so this is the instruction buffer, scheduler and dispatch unit, and data is coming from here, and basically data is getting, this is SIMD and this data processing. So, computing and data and load store, and I am going to skip all of that, but I want to go back and tell a story before I end. So, all of these names are of some scientist. So, I am going to highlight my favorite scientist and I am going to ask you, this has nothing to do with GPU, and ask you how many of you know about this scientist? Those are, how many of you are from computer science? Thank you, at least somebody knows. Women's Day was like few days ago, you guys should be ashamed of yourself. First female lady programmer. There was a language we had to learn in the Fortran COBOL, there was a language called Ada, it was a predecessor of Pascal, again that language also named after in respect to Ada Lovelace, and she was even today is the same problem, but in those days females were so utterly disrespected, they would not get Nobel Prize, they would not get any recognition. So, I think it is a high time we kind of change that attitude and figure out, she was given the task of maintaining, I guess this is the Babbage, the computer, it is a full room full of big computer, it is basically think of a calculator, a room full of size, her job like a female, yeah, right. So, they thought what a female can do. So, just take care of this thing. So, her job was to do just compute 2 plus 3 using this big machine, rotate the knob here, push that handle there, kick here and bang your head there and those stuff, that was her job. She took a notepad and tried to do little annotation, and she figured out a lot of some of the Bernoulli equation and all that stuff. She figured out we can compute lot of stuff if we do these set of steps, and she noted down some of those footnotes. We today treat them as like first program. Technically she never wrote a program, there was no programming language, but simple annotation in her notebook, and it is actually amazing if you go back and read those stories, and I actually feel bad for the men in those days, and all of those are so powerful that this simple calculator, if you follow these steps, you can compute Bernoulli equation, this and that. So, basically you can do lot of stuff beyond simple calculation like a calculator. So, you annotated all that, and later it took the whole community, like this is in 1800, it took whole community like 200 years to figure her contribution, and basically language is named after Ada language, and this was Nvidia. So, Nvidia did one good thing, this 2021 they named after her. We stop basically here today, and in the next lecture we will start talking about little bit of hardware acceleration and mostly about how do we use some of those acceleration techniques for explainable AI. Thank you.
So, we will have 30 minutes tea break, we will assemble again at
খাবার এটা পালাবো
কোথায় যাবেন?
খুঁজে Good morning. In the previous lecture, we talked about different ways of accelerating your computation, and we briefly looked at how do we modify the current processor architectures. We also looked at how do you use field programmable gate array, and finally, we looked at graphics processing unit. And as we are going to talk about now tensor processing units. Before I talk about that, most of the acceleration of AI today is happening through graphics processing unit, and Google is basically this tensor processing unit is they are trying to create a competition, but GPU is still far ahead. So, let us talk about tensor processing unit. The key idea of tensor processing unit is a slightly different idea than what you have seen. The idea is called systolic array architecture. This is again from 1960s IBM days. Now, this got popularity, but because of the idea that how your neural network is. If you recall, we talked about different nodes and multiple layers, and some of them are connected differently, and then there are nodes, and finally, the prediction. This is where inputs are, and each of the edges you have Wi different way. This could be W0, W1, W2, and so on and so forth. What each of the node is basically computing is summation of Wi xi. Xi is 1 if that link exists, xi is 0 if that link does not exist, Wi is the weight on that edge. And during the machine learning process, the machine learning model basically learns that weight. So, the idea of tensor processing unit is effectively how do I compute this multiplication, because effectively if you are using neural network kind of machine learning model, it is nothing but multiplication. To be more precise, nothing but matrix multiplications. How do we do matrix multiplications faster? That is the bottom line. It just so happened AI, as I go along, when I talk about explainable AI, I will show you it is basically nothing but matrix manipulations. So, therefore, if we can do matrix multiplications faster, that is basically the acceleration. The difference between FPGA, remember FPGA can accelerate anything on everything, and if you want to accelerate your explainable AI, that is good too. Processor can run any program. If you want to run your multimedia program, that is fine, we will give you multimedia support, but this one can only do or effectively do matrix multiplication. The way the idea works or systolic array, instead of spending and telling you an architecture course, if some input comes in here and if you compute something, that computation would be used by this cell as well as in this cell next time step. When this cell is done, it is going to provide this cell and this cell. When this cell is done, it is going to provide this cell and this cell. So, if you think about it like a waveform, if you throw a boulder in the river or pond, it creates that ripple. It is basically that ripple. In first cycle, these guys are computing. Second cycle, these two guys are computing. In the third cycle, these three guys are computing. In the fourth cycle, I do not remember 4, 5, 6 whatever the next layer. That is how computation progresses and final result goes through these layers. Now, you might think how is this helping? Remember in our original design we are computing this Wi for this node, but whatever we computed that is getting used by the weight multiplication for subsequent nodes. It is the same computation that is kind of percolating. So, whatever computation you did, and let us say you got a 5, from here that is the value that is getting or multiplied by certain weight, that is the value that is propagating. And if you try to recall how AI algorithm works, color is a feature and that has a more weight. So, computation kind of percolates, and if you can effectively do that faster, that is the systolic array architecture. Any of you have any confusion about this basic idea? Only thing I tried to highlight, how is it systolic array architecture, how is it different from other computations? This is not a generic, this is going to accelerate only if your computation or your program has computations like the neural network, only then it is powerful and useful. If you have a AI model or architecture that does not have a computation propagation, then it is not going to be helpful. It is not a general purpose acceleration like FPGA, it is not. So, this is very customized for accelerating neural network type of AI models. Any questions? Now, let me just zoom into little bit of the important aspects. So, this is basically this one I just zoomed in this box matrix multiplication, and I am trying to show what is happening. But in addition to matrix multiplication, there are few other interfaces, control, high speed data transfer, different types of buffer and interface and all that stuff. The reason these are needed or all this stuff, because remember, when you are operating on AI algorithms, it is used by somebody. If you think of a car, what is the input to the structure? In my class I am just saying, well, the input comes somewhere. Where does it come from? It comes from, in case of car, from sensors, the distance between the car, current speed, all of that contributes to the value. So, these are the values, analog values coming in, or sample discrete version of it. Those are the values, different types of sensor data coming in. That is why you need all kind of different types of interfaces and controller to do the data acquisition at speed, and then computation would be happening here. Then the result, whatever decision, slow down, what is the decision in the car? Either apply brake, so maintain the distance, or you just, if it is a upslope, increase the fuel injection to maintain the cruise controller speed, for example. Or if you are going down, then decrease the fuel injection rate, so that it does not speed up beyond what you asked for in your cruise controller. So, those are the aspects, but I zoomed in only into the middle part. Any question on this? So, now I will show you the, I hope this animation will work. So, what you are going to do, every clock tick, which is a clock cycle or a time step in computation, the system clock data is passed to each processor from two different directions, then it is multiplied and the result is saved in a register. So, here are two sets of data, from one from this side, one from that side. Remember, we were trying to do Wi times Xi. So, this is a matrix, this is a weight data. So, you can visualize it, although this is not what I am illustrating. You can think of this matrix is this one and this matrix is this one. You have tons of edges, nodes, and millions of them to be precise, and they are coming from two sides. And as you will expect, so this set of values 342, 255 and all that thing, and 3. So, this 342 is basically this 342, 255 and all that, whatever, 253, 325. So, this data is basically this data, and this data is basically this data. Let me see if that is what it is, 323. Yeah. So, this is 323, that is 323. Now, so I want you to understand one thing. So, this basically 342 is basically this 342, and here 323 is basically this 323. And the reason this way, if you recall matrix multiplication, the way it works, row and column. Now, as you, if you already have a good visualization power, you basically know these values would be pushed in from this side, which I will show in animation. These values would be pushed through this side. But normally you do not have to worry about it. I am showing you internal details. As an user, you simply put your AI algorithm and it would run on the TPU if you have a TPU. And these days you can buy TPU even in your USB drive. So, you can connect a USB drive, even if your computer did not come with the TPU, it would still work. Okay, so, let us see if the animation works. So, 3 and 3, and these are shifted by time step, these are intentionally done, and then 3 and 3 is supposed to come in. So, here I circle 3 and 3, those 3 and 3 is going to get into this P1 in the next cycle, that is the 3 and 3, and everybody else accordingly moving. And when this computation is done, you realize things would be moving on the right as well as down, and that is what is supposed to happen, that did happen. And then next set of values, so 4 was here and 2 was there, they are going to come down and they are going to compute, and then that computation again going to percolate, and this story will just keep continuing until the 5 and 5 gets in and compute, and when there is, oh, I forgot to tell you that the results of P1, P2, P3, whatever that result is supposed to be, these numbers, if I go back, you will see these numbers are getting generated, added. Let me go back. So, initially it was started with 3 times 3 9, even before that it was 0. So, 3 times 3, that is basically 9, and then once 4 and 2 comes in, that is going to be 4 times 2 8, that would be plus 8. So, similarly every computation, so you are basically going to have, so this is basically P0, P1, P2, P3. So, there are 9 elements, those are the 9 locations at the bottom. I am just trying to show what is happening in those values in a time step, and those values are keep on changing as values are progressing, and if you look and compute, you will see those are correct, and that is basically the final result you are trying to compute. So, what does this achieve you, this type of computation? So, in 2n plus 1 clock cycle, you will be able to compute it instead of n square, that is the speed up, theoretical speed up. Normally, if there are n element matrices, you would have need n square, but because of systolic array, 2n plus 1 is basically linear time computation of a multiplication, right. So, so far we basically talked about how do we accelerate different types of computation. Some of them are special purpose like GPU and TPU, some of them are generic like improving the CPU processor architecture or FPGA. Now, I am going to talk about how do we use this acceleration to speed up explainable AI, and there are a lot of works. I am going to zoom in into 1 or 2 of them or touch little bit of them. So, basically think about actually there are a lot of works. If you want to write paper, let me illustrate how you would write paper. You can do acceleration, here I am talking about 3, but actually you can do 4, and there are so many explainable AI algorithms, popular ones are 3 or 4. So, 4 times 4, there are 16 choices of paper. All of the combinations are not done yet as of today, right. So, there are 16 papers you can publish, but some of them has been done, most of them are on FPGA based. So, I am going to show only one of them. So, I am going to pick up hardware acceleration of the model distillation. If you remember in the explainable AI algorithm, I talked about decision tree is one of the simplest one. Model distillation is somewhere in the middle, then we have Shapley value analysis, then you have integrated gradients, there are so many algorithms. I am going to pick a middle one just to kind of illustrate, we have all these parallelism, why do not we just run this program as it is in parallel, why that is not good enough, I am going to illustrate that point. Or specific to explainable AI, what does parallelism mean, which fabric do we use, and if we use that fabric, what exactly do we do. So, I am just want to illustrate 1 or 2 of them, but before I go there, I want to talk about acceleration and AI. AI acceleration is happening almost for 2 decades, and in fact, GPU is inherently what it does is AI acceleration. Today, all the GPUs that comes within your computer is basically tuned, super tuned for accelerating any AI algorithms you are running. So, that is why I intentionally decided not to talk about AI acceleration, then I will be talking more GPU, which we already did. So, what we talked in GPU is nothing but acceleration of AI algorithms. What we talked in TPU or systolic architecture is nothing but accelerating AI algorithms. Now, what is the difference of AI and explainable AI? The additional explainability, and the explainability, whether Shapley value analysis, whether model distillation, it has a lot of extra equation in addition to the equations you have or matrices or matrix operations you have for your AI model, and how do we make it faster. So, I am just trying to show you, this is one of the recent work, I am trying to show you what are the opportunities. So, in this particular one, you basically have trust transformation. So, original computation that I wanted to do, that is not parallelism friendly. So, I want to transform and modify it. I will show you some example. Then some data the data I am dealing with, I want to decompose it, then parallel computation should be no brainer. Wherever you find a parallelism, you perform that computation, right. So, task transformation. So, basically as you realize in model distillation, we also had the same thing. If you recall the model distillation, we had model distillation, we still had, remember we have the task we want to perform, and then on the top you have normal ML model, and then in the bottom you have the distillation model. You have the distillation model, and normal model, if you remember, they also look like this neural network and so on and so forth. These also look like neural network, right. It is a bunch of neural network. So, that is basically the distillation. So, we are basically talking about accelerating this one, but as you realize that is still a neural network layer, and that is still kind of a matrix multiplication story. So, in that context, so basically it boils down to still you have bunch of nodes, different weight, and you are computing the weights with that particular edge, if that edge exists, and which boils down to again some weight matrix, and this particular is the corresponding node values matrix, and to compute whatever result you are trying to compute, that is the matrix multiplication you are computing. So, the in terms of, so that is basically the matrix representation, and when you are transforming task representation, remember we are multiplying the, this is the input x, this is the input x. If you recall again, what is the, where is the input? So, from the original layer, this is the input. For subsequent layer, whatever it produces, that is basically the input for subsequent layer. So, input, and then you have the kernel k, and that produces the output y, right. So, kernel k is basically, think of weight matrix. So, what we are trying to then compute, we are basically trying to compute this particular one through Fourier transform, and the way I want to explain this in layman terms without getting into the mathematics. So, somebody in the community already has shown, if you have any computation in Fourier transform domain, if you are not from electrical, you may or may not know, but in the Fourier transform domain, if you have certain computation, then converting that to systolic array computation, there is a natural mapping. So, somebody already established that. So, what was existing, if you had something in the Fourier transform domain to systolic array architecture mapping, that existed. So, what we had to do, whatever explainable AI model we have, the distillation model, if we can map it to Fourier transform, then we can make use of it. Now, as you can realize, this is, I want to go from nose to the eye, I actually gone to the head, then to the ear, then came to the eye. If any of you could find a natural mathematical way of mapping this, that would be much faster and better acceleration. So, that is an opportunity for you to do research. But nonetheless, this is the mathematical transformation, you are doing a convolution operation. So, this is the task transformation. Our original computation was something, but we are transforming it. The reason we are transforming, as you know, somebody already showed how to go from Fourier transform domain to systolic array domain. We were just basically converting our activity into Fourier transform computation, and all these equations basically nothing but that is what it is doing. So, all I want to make sure you understand, this path existed, this is your destination, this is your source, your home, that path existed, there is a bus, train, whatever, all you have to go from this point to this point, that is all we did. Yes, please.
Sir, normal Fourier transform or DFT?
That is an interesting question. I do not know, I can check and tell. Is there a difference between normal Fourier transform and discrete Fourier transform?
Normal means I am talking about continuous Fourier transform.
Okay, so, this is going to be a discrete Fourier transform, because we have discrete values of weights and edges. Yeah, this would be discrete Fourier transform. At least I learned something today. Okay, all right. So, you could tell I do not have electrical engineering background. Now, any other questions on this basic idea of why are we doing task transformations, because we do not know how to go from here to here if I want to use the tensor processing unit. So, the next step, is data decomposition. So, again a lot of equations, I am not going to get into that. So, basically for the 2D discrete transformation, we are applying on this M and N signal, and you are trying to divide this data in such a manner so that it parallelism friendly, which is what we are going to do the next step. So, we are basically transforming, think of matrices, forget about this equation, we have bunch of matrices, transform all the rows of X input to obtain the intermediate results X prime, and then transform all the columns of resulting matrix X prime. So, basically this data transformation, so this is basically each of the row we are transforming in the X and in the resulting each of the columns. So, each row I and column j, that is what we are kind of obtaining, and what we are able to show through these equations, that these operation on these rows and columns are independent. So, therefore, you can perform them in parallel. If you have multiple core, multiple TPUs, you can perform in them parallel. So, it is not like okay, in a matrix multiplication, when you think of any matrix multiplication, not for this particular AI, when you think of you need to do multiplication of this row with this column, and there is some kind of implied understanding I need to keep multiplying this element with this element, next one with next one, and so on and so forth, as if there is a sequentiality. Even if that is true, this one with this column and then this one with this particular column, all that can happen in parallel, and eventually when you add it up, that is fine, but those activities can happen parallel, and identifying those parallelism which compiler may not be able to identify. Then finally, when you do parallel computation, then basically all these different types of matrices or their different elements, you could technically, depending on how many cores you have, you could technically take each of the element for each of them for let us say multiplication or whatever you are doing, perform the computation, and then you kind of assemble. I colored them so that you kind of see where the computations are coming from, and then you are assemble them to get the from the remember we are trying to go to the Fourier transform domain. So, from the normal matrix multiplication to Fourier transform domain, once we have the data decomposition, we will be able to make use of different computing nodes and run them in parallel. So, if the basic idea is clear, you will be able to kind of do, and most of you or those of you who are doing multi-threading, these ideas are kind of similar. Only thing is what we did, we took the explainable AI algorithm or model distillation problem and those matrix multiplications, and for that specific applications, what are the application level parallelism opportunities, I am just highlighting that. But you can just take your computation, give it to a standard parallelizing compiler, that compiler might be able to figure out all of these itself. You do not have to do any of these manually or explicitly. Now, how well does it work? I want to just kind of highlight how well does it work or who does work. Of course, remember this particular program is little biased towards TPU, because I picked up model distillation. If I pick up Shapley value analysis or somebody else, then GPU would so much better. So, in this example, as you can show, I am going to show different kind of data sets. So, this is basically GPU versus CPU is this one. So, GPU is faster, like for this kind of total performance per watt in same amount of energy, which one is giving better performance. So, GPU seems to be showing 2 times better. TPU is compared to CPU 16 times better. So, 2 over 16, that is like this should be directly TPU over GPU is about 8.4 times better in terms of total performance per watt, and GM is geometric mean and weighted mean. But anyway, so point here is actual numbers are not important. So, incremental is basically excluding CPU power, and because we ran all of these experiments on our normal devices which had GPU, but remember CPU is also running there. So, to really get the real performance of GPU, ideally we should somehow subtract the contribution or whatever CPU is claiming, trying to just identify or isolate how much is exactly GPU taking, how much is TPU taking. That is the way we kind of try to do experiments, but whichever you want to do you can do, but no matter how you do, the numbers will kind of change. If you 2 times better, instead of kind of in this particular case 8.4 or 13.8 in this kind of example, weighted mean and geometric mean. So, in the bottom line in this particular analysis it shows, and as expected TPU is going to do better than GPU and GPU is going to do better than CPU. But as I said, if you go for another explainable AI model, the chances are and this experiment was done 2 or 3 years ago, in between GPU has gone through faster parallel computation. What is the relationship? Relationship is right here. So, relationship is we are trying to compute model distillation problem. So, starting problem is we have an explainable AI model that we want to map to TPU. In this context, let me put all the terms you said. TPU operates on systolic array architecture, that kind of very friendly natural representation of neural network. Now, somebody in the community already showed how to do Fourier transform to kind of systolic array mapping, which basically means TPU mapping. So, what we kind of did, took the model distillation and mapped it here. It is not anybody is better, it is basically a sequential relationship. We basically took our computation of matrix multiplication, mapped that to Fourier. Now, parallelism is orthogonal to any of these discussion. You can do this computation without considering the data partitioning and parallel computation, or you can do this. So, the parallel computation help, can I use 2 TPU, 4 TPU, 6 TPU, 32 TPU, can I make use of that? If you are using 1 TPU, parallelism does not even come into the story. If you are using 2, 4, 8, 32 TPUs, then it is basically saying you do not have to treat it as that matrix 1 and matrix 2, you can deal with column 1 of matrix 1, sorry, row 1 of matrix 1 and column 1 of matrix 2, row 2 of matrix 1, column 2 of matrix 2. So, then those can go to TPU and systolic array, and that can happen in parallel. So, parallelism is orthogonal to this idea. Any other questions? So, in terms of scalability, so scalability basically means the problem size of the matrices. If you keep increasing think of size of the neural network. If you keep increasing, who scales in what way, and as expected when the problem size, remember the weight matrix multiplied by the AI matrix. So, that is the weight matrix and that is the other matrix WIXI. So, the CPU is going to very quickly going to take a lot more time. So, this is the time axis, this is the how complex those matrices are, how big that neural network is, it is going to be extremely slow, and that is expected. Now, in this particular example, remember this was done 3 years ago, this particular example GPU is kind of not as bad as CPU, not as good as TPU in terms of problem scaling and the time it takes to compute. And again remember 2 things are in advantage to TPU, it is 3 years ago, GPU was not that level as today, and second thing was this particular problem model distillation is more friendly for systolic array computation. So, this was a bias towards TPU. So, basically basically to kind of this is a conclusion for today's lecture. So, there are lot of widely used hardware accelerators methods. So, field programmable gate array, graphics processing and tensor processing, and explainable AI algorithms are complex, and unless we utilize kind of acceleration, they are not suitable for many real world systems. So, basically in the next lecture we are going to talk about malicious software malware and discuss how explainable AI can be used for malware detection. So, we have a lot of time, anybody want to discuss questions, go back to any of the material or make the connection, I will be happy to talk. Do you have any questions? Go ahead.
Particularly Fourier transform maneuver was do. So suppose we are doing polynomial multiplications. Suppose you are doing polynomial multiplications. Polynomial multiplications is suppose you want to multiply two polynomial of order n size. It is actually order of n square complexity. But if you convert into Fourier domain, then converting to Fourier domain, one polynomial will take n log n time, another polynomial n log n. So it can be done in n log n time, and multiplication in Fourier domain is actually additions. So now instead of multiplying, you are doing in actually addition domain. So addition of two polynomial, it can be done in order n time. So effectively, order of n square algorithm is getting converted into order of n log n algorithm. So can here also it is doing similar kind of thing. So multiplication is order of n cube or matrix multiplications.
Right. So the question is interesting. Question is, if we map a problem, matrix multiplication problem to polynomial manipulation problem, so then you could potentially convert into multiplication to addition, or order of n square to order of kind of n log n problem. And if I do tensor processing or systolic array, that's kind of order n problem. So then question is, are they conflicting idea or compatible? They are actually compatible, because going to Fourier transform domain or that computation or the way systolic operate, so it's actually same. The way the computation or the flow of data, it's actually systolic array computation. That's why when I said the mapping existed, that Fourier transform you can naturally map to systolic array. So in other words, if you go through Fourier transform domain, instead of order 2n plus 1, it's going to be order 2 n log n plus 1. So if you go directly, or if somebody can find a direct way of going, it's order n. If you go via Fourier transform, it's going to be order n log n, because mapping of n elements or n square element, it takes n log n. So it's basically order n log n. It's slightly more complex than if somebody can figure out directly going to systolic array mapping for the explainable AI.
Can you think of a serial algorithm? So because matrix multiplication complexity, serial complexity is actually n to the power 2 to the power 6 1, I think so. It's not n cube, but n to the power 2.
Little
If you do Fourier transform, then it can be done in lower, but no one have reported kind of thing. It may not be directly possible in terms of, but exactly may not be possible maybe.
Okay.
Otherwise, theoretical result may change.
Yes, absolutely. There was another question here. Somebody. Yeah, go ahead, please.
Sir, I am little bit confused in data decomposition thing, like how it is connecting with the task transformation and parallel computing.
Okay. The question is the task transformation, and that's why there is this first overview diagram. So data decomposition, task transformation is basically you are taking an explainable AI algorithm and converting into matrix multiplication algorithm. That's it. So if you are standing at this point, you actually don't know whether it came from AI algorithm somewhere else. All you see here, bunch of matrices, and you are doing multiplication of them. That's what we call it, task transformation. If you want to call it something else, it's fine, but basically you are taking some concepts of neural network and you are talking about matrices. In fact, in the AI domain, it's all about linear algebra, manipulation of matrices. In fact, now that we have time, I can talk about little bit about quantum machine learning. Even in quantum domain, it's all about manipulation of matrices. It's just that the elements of those matrices are different. Any other questions?
I have one question. So,
Sure.
And I have seen many work that try to map this a trained model into FPGA, right? So it can be for explainable AI, for any other ML model. But usually the training process never been done on FPGA, right? So, I mean, I have not seen much work that try to map the training process is also an algorithm, right?
Right. So interesting question. The question is, we talked about different acceleration algorithm and we talked about all of this stuff, and what I did not talk about or kind of implicitly assumed that all of these acceleration I talked about, it is about the trained model, whichever will do the final computation. So, if you recall, in the AI model there is the training part. So, there is this training component and then there is this prediction or final deployment, whichever you want to talk about, where you basically make basically prediction for classification or finding a value for regression or whatever type problem it is. All the acceleration I talked about, I forgot to mention, it is all about this one. You accelerate this one, because nobody cares, or mostly nobody cares about how much time, how much effort, how long you take in the training time, and training today is de facto in GPU. This is de facto, but for this deployment or prediction we talked about various choices. We talked about FPGA, we talked about GPU, we talked about TPU and all that stuff, and it is quite possible eventually these also will be default. Oh sorry, I mean these days many people use FPGA actually more than GPU, and the reason is GPU is trying to do certain computation, but you still have all these data movement and all that stuff, but in FPGA you just program whatever the model is once, and that is the thing going to keep on running. It is like then you kind of formed a hardware which is supposed to run faster than GPU, where things are moving around with the inputs. So, most of the people are kind of try to use FPGA here, and here of course the de facto is GPU during training time. This is the same analogy of compiler in embedded systems. You can take as long as you want to compile, but when you compile the code, that need to be tiny, small, fast, quick, that is this idea. Any other comments or observation? Otherwise I will use the remaining time to talk about quantum machine learning. No questions? Let me use Professor your suggestion to use W. Nice. So, we will go for, is there any way to pull up that slide? Is that much easier? The quantum machine learning slide from, it should be there, no, not today, in yesterday's thing. Let me write it, that is better. So, how do I go there? March, you have to get out of once.
This is March yesterday.
Oh, March 10. Cybersecurity, explainable AI. Let us go for this one, explainable AI. Go for that thing. Somewhere explainable. Go up, please. Up. There should be a right there. Yeah, this one. Just click on it. This is much easier. So, I want to talk about quantum machine learning, because we are giving background of different type of machine learning model, and we talked about different machine learning model. So, it is just kind of assumption is it is all used in classical domain, but it turned out even in quantum domain this is used, and this is very useful. And in fact, in quantum computing one of the major problem is reliability of the qubits. It is very unreliable. So, the way it works, whenever you build a circuit, quantum circuit, I will not get into the detail, just think of it something, and this is a parameterized double quantum circuit. If layman terms you want to think of an adder, it can add any numbers, think of that way, but that is not true. Any number, integer, floating point, character, it is like reconfigurable adder, reconfigurable gates, reconfigurable nodes. Once you have that computation, then you want it to compute something, but it is not reliable. So, you have to run that computation again and again and again hundreds of times in a hope it will produce the correct result. And the way people use today, is, what did I do? The way people use today take the help from classical computers. So, think of this is a quantum processor and this is a classical processor. So, quantum computer and classical computer is sitting side by side, they are connected. So, classical computer will measure what are the values from the measurement of the quantum computer, and then it try to figure out are you walking in the right direction or you are walking in the wrong direction. If you are walking in the wrong direction, then it is going to feed some information back here, and think about it, the parameter it will tune. So, when anybody talks about quantum machine learning, it is not a machine learning algorithm running in the quantum hardware. There are some research, but mostly to speed up machine learning using quantum computer, but our computers are not there yet. For academic purposes, for publication, that is okay, but in reality this is what works today in the industry, commercial scale, is that classical computer is running the machine learning, classical machine learning, and then, and I remember all the acceleration, explainability we talked about, it all fits here, and then it will give the feedback how to tune the parameters so that it goes in the right direction. If you think again the same gradient descent, it is just making some transformations and setting the parameter. So, in reality you are initializing the quantum parameters with something initially, let us say you initialize with some random state, then you let it evolve for few seconds, and then you measure and you say if it is going in the right direction, if not it will initialize to something else and let it evolve. So, you want to take advantage of quantum computer, which is exponential speed up in certain class of problem, but you still need the help of classical. Now, this is kind of a fallacy, because classical is exponentially slower and this is supposed to give exponentially faster, but you need to do hundreds of iteration. So, your speed up is bounded by the speed of this, but that is today. When quantum computers should become stable, reliable, then you can take this out from the picture. Anybody has any question on quantum machine learning? So, all the ideas we heard in the machine learning, you can use all of them there, and you can use quantum in your resume. Yes, please.
Sir, I have a question, but the problem with me is that I raised too many questions and some of them might be irrelevant to this context. So, we are now talking about quantum machine learning, and maybe quantum the speed up is possible because of quantum superposition.
Superposition, entanglement, all those stuff.
My question is, why classical computers have not the phenomenon of superposition but quantum computers have?
Okay. So, that is a question for the physics people. I am sure
yeah.
there are some physics people, but I can explain that in layman terms. So, this idea of superposition or this quantum phenomena, as the Feynman, whoever the father of quantum computing said it, I should not take an analogy. Any analogy I take from classical world, that is wrong about quantum phenomena. So, this is a quantum phenomena. Actually, there are some other phenomena too, which is topological quantum computer uses that phenomena, and that phenomena is, there is another physics behavior where they call it anion. So, these are qubits, classical computer is bits, and there is another physics phenomena, funny phenomena or magic phenomena called anion. When two of those anions meet, either they self destruct or they entangle and start making dances. So, dances would be 1, destructing each other would be 0. That is all they do, there is no other way of, and generating them it took I do not know how many years, and Microsoft just demonstrated few months ago the first topological quantum computer. So, that is a different phenomena. For quantum computing, which is stable for quite some time and people are using it based on quantum principles, it does not rely on electrons or electricity flow on and off. It is a phenomena of quantum effect, that is the superposition, which is not 0, not 1, a composition of 0 and 1 at the same time. In fact, in the extreme case of that is classical computer. It is a composition of, so any qubit can be explained as, any qubit can be explained as, any qubit can be explained as alpha 0 plus beta 1. So, such that alpha square plus beta square equal to 1, and if you think about the extreme case, once you make alpha as 1, beta as 0, that is basically the classical case. But it is just that if a system or a qubit is in a quantum state, you cannot control it to that. It would evolve or compute itself to a specific set and initialize it, and out of those exponential space where they would be in composition, one of the space is only 0, one of the space is only 1, two extreme. In between it is in a interesting composition of 0 and 1 at the same time. So, in a way if you think about it, quantum computer is a superset of classical computer, but that is actually mathematically wrong statement. Feynman said, no, do not take an analogy of, only analogy I can take to visualize it, the Schrodinger's cat example. So, there is a box you cannot see and there I can't draw a cat, I am just saying, think of this looks like a horse. So, there is a cat inside the box and there is a apparatus which has a poison, and if the cat is smart it would be open to open that lever and drink the poison and die. If the cat is dumb, then it will not be able to open it and it would be alive. It is a soundproof box. So, once you put all of that in and then if I ask you, it is your cat, what do you think, is cat dead or alive? That answer is it is in superposition state. You cannot say it is dead. If you are the owner, you will think your cat is the smartest. So, therefore, cat should be able to open that lever and drink it, but as a owner you are like a father or mother figure of the cat, you do not want your cat to die. So, you are not willing to say it. On the other hand, if you want to believe cat is alive, then you have to assume then cat is definitely dumb, and as a mother or father, when do we say our kid is dumb, right? So, it is that interesting phenomena. That is the only example we are allowed to take on quantum computer to connect to classical world. So, it is basically at any time the cat is either alive or dead, none of them are true, it is in a mixed state. But you and I know in any real world object there is no in between states, even if it is suffering and tremendously suffering, either then it has to be alive, it cannot be alive and dead at the same time. But in quantum world that is what it means, you can't say it. Any other question? Yes, please.
Sir, for qubits it stay for a very little bit second. Yes, it's very vanish. After some time it vanish. The value of the qubit also vanish. Then how it is they in quantum machine they calculate? Because in qubits the value also vanish after some time.
Right. So, the same thing happen in classical world. Why you are not worried about it? In classical world, any transistor you have, if you so let us take an example of a transistor. So, I will come to and answer your question. So, if you have a transistor and it is connected to your supply voltage, this is ground. So, let us say you set it to 1, even if you cut off this so officially you cut it off, it would, because of leakage current, it would still leak. So, if you are thinking this as a capacitor or effective capacitor which is a value 1, it is still going to leak the leakage current depending on, and this is a serious problem in today's 3 nanometer, 5 nanometer size gates, it leaks. And that is why every 8 to 20 millisecond the refreshing is needed in DRAM circuit. When DRAM you buy and gives you a calculation or number, that speed of this memory or access speed of this memory is this much, it actually includes that refreshing time. It is like people are eating on the table and they have a water glass and there is a leak on the glass. Somebody has to move with the jug, keep filling the water. So, that leaking effect is even there in, and then there is mechanism. In qubit, sure, qubit also has same phenomena, right? Even if you entangle, that entanglement frequency goes down, all those problems are there. But we have a bigger problem in today's qubits, they are unreliable. Not that they are leaking or losing, people are not worried about that yet. People are going to do measure within that time and do the computation. It is basically you are trying to make somebody to go to certain composition state and it is going to some other state, it is going to some other state. And the worst part is you ask it to execute 100 times, every time it goes to different possible states, because the speed up you, exponential speed up you get, because everybody talks to everybody. But that is the cause of reliability. If you have a room full of kids and everybody is talking to everybody, can you do any meaningful computation out of it? Can anybody figure out what is going on? So, that noise becomes a serious problem. So, mathematically it is powerful. So, the right now the problem you actually mentioned, that they hold whatever stuff for a certain time, that is not a problem. Right now problem is the electric pulses we kind of send, to each of these qubit to program, although you know what pulse is needed to program what the qubit, depending on whether it is the morning or evening, the mood of the qubit, how much they are talking, this pulse is not going to be enough. So, you have to keep trying different pulses. That is basically the problem. If you have no other questions, we can stop here, right. Thank you.
Okay, so we'll come back at 2:30 p.m. As announced, we'll start the second half at 2:30. Take time to have a good night.
So, here is a brief outline. I am going to talk about why do we care about malware, then I am going to introduce you to some of the malware kind of families, and then I am going to briefly talk about malware attacks, not so much about from a software perspective how it affects the society and economy and the ecosystem. So, malware is a broad name and it is an abbreviation of malicious software, and it comes in various form. I am going to zoom in today into each of them, and they have different names, whether software trojan, virus, spyware, adware, worms, crimeware, rootkit, and although name may seem and sound different, they actually have some inherent commonality. It's basically a program. So, then there are two aspects that as we go along we talk about. How do they get installed in your computer or device, who are the people making it, and basically what is the economic benefit for them, and the third aspect is as a researcher what can I do, where do I start. So, when I started many years ago, when I started there used to be a web page maintained by I do not remember some European or Russian organization, virustotal.org or com, and that they used to maintain all known viruses or malware and their solutions and their defense and attack. It is same as common weakness enumeration website. It is kind of was owned by a private company, private party. If you want to download for your research, then you have to pay to them, and we downloaded many of those, and all of them are actually real malware. You download it and you run it in your computer, you will get affected. That is why many of them we have basically downloaded in a sandbox environment. So, you basically create a kind of a virtual machine environment, very protected environment, and within that environment you execute them. And the way they spread, it could be web bound when you are downloading something from your email, you are checking a website, or it could be any mobile devices, it could be you are connecting an USB, and as I go along talk about some of the very popular malware in terms of what kind of chaos they have created, in terms of the monetary damage they created, you will see they actually there is a social engineering aspect to it. It is not just a program and oh oops I hit that link or I downloaded that or executed that, there is a social engineering aspect to it. So, if we go by raw numbers, so this is by Bissell and Pomen Institute. So, if you look at the numbers, of course, in this classification they divided the malware category, one of the category they call as malware, then denial of service, web based attack, phishing, malicious code, stolen devices, ransomware, botnets. We will get into all of them. Anybody knows what is a phishing attack? Yes, please.
It is a targeted attack wherein the victim is made to, for example, click on a link. When it clicks the link, then a spurious website can open.
So, how a phishing attack is different from other forms of attack?
Because it is targeted.
So, targeted would be, so for example, common phishing attacks are let us say you posted something in your LinkedIn, Facebook somewhere, and people kind of know you visited one of the party, only other people everybody assumes knows their family member, and let us say then I call your dad or mom and pretend I am calling from you or as your friend, oh XYZ was in this party, fallen sick, I am taking to hospital and needs immediate surgery, this much of money. So, the reason that is phishing or targeted attack is that you as a parent, you would tend to believe, oh yeah, my son was in that party on that day, and this person has a friend of that, and that friend is calling. So, it becomes realistic, not just oh I will make you rich, and that does not work. Even bigger targeted attack would be I would pretend as you when I call your parents, to the extent I will have a mimic exact your voice, because large language model needs only few seconds of your voice sample, and each of us think we are great singers, right, great singers, actors, we are posting on the web, and that is our disaster. Our pride becomes our disaster. So, then even a few seconds of your voice sample would be enough for a large language models. I can use large language models, I will be speaking like myself, and then I will use large language model to transform my voice to your voice when I call your dad mom. So, it would be exactly your voice. If that is not enough, I will call them on their WhatsApp and I will appear exactly like you. When I open my WhatsApp and start calling your parents, they would look face to face you with your all facial expression and everything, or I need a few seconds of video. In fact, few seconds of static image will do, large language model will convert that to video, and then when I am talking it would be exactly you talking. And even worse, within if you have a few minutes of your video sample, large language model will be able to figure out what are your idiosyncrasies, like once in a while you scratch your right chin or left chin, or you are clicking here, any of the idiosyncrasies you have, I will be displaying that, such as dad how are you, and if you never said that to your dad when you called, and if I try doing that, that would be red handed catch, what is going on, it does not, that is not my son. So, everything would be picture perfect. I will be able to do the phishing attack better than you, the way when you talk to your family. So, therefore, please be careful anytime you post anything. I know Dr. Karfa is going to post all of this video in this, that is not a good thing. So, that is the social engineering aspect. As I go along, you will see how social engineering also helps in spreading this. And then there is issue, if you like this video, put a like on it or forward it, that is also social engineering. Not only you are getting scammed, you are also spreading it to scam other people. And some social engineering are based on religious belief, or if you do not forward it to 20 other people, your kid will die, or some kind of nonsense, and people tend to believe that, a lot of people tend to believe that, and then that is how the social engineering lets the spread of that spam or malware. So, that is basically phishing, but all others, no matter what it is, which of you can say what is denial of service? Yes, please.
So in denial of service, basically there are two types. First is DDoS, in which we overwhelm the system so that it doesn't give output. Basically, we are targeting that availability part in CIA tried.
Thank you. So, denial of service attack, depending on you are denying what. Let us say it is a website to register for a PhD program in IIT Guwahati, and you want to do denial of service attack, and then all you have to do is first you apply, make sure you apply, your application goes through, and you make sure nobody else can apply, and you keep saying fake things, and system will say, oh, you did not enter your birthday correctly, you can't be born on 1940 or some good check. You keep doing that billions of requests per second, so that admission or registration systems get overwhelmed, everybody else get to wait or timed out or system is busy or something. But the claim is your malicious things should be able to access and try entering, other people will not be able to enter. If you are not able to enter, then other people will be. So, that is the denial of service attack. In fact, there is a social engineering aspect of it. Many years ago in Jadavpur University, computer science department, the people who got registered or actually got the enrollment is more than 500 scores. Normally top 100 used to get admitted, and it turned out there was a student from South Point High School whose score was really low, I do not remember, 300, 400, and that person was determined to get it. So, that person and their family member went and distributed leaflets saying how many computers in the computer science department have and how many have viruses, not on disk is needed to clear that, and it is not a department worth going for, it is a useless exercise. So, first 300, 400 people did not even enroll in that year. Now, of course, you may think that social engineering will fail, all the professors would be angry at that student or something will happen, nothing happened, people forget. So, that is the social engineering aspect of it. You can do cheat and fraud, yet, and similar social engineering happened in USA. So, two big film stars basically wanted their kid to get admitted in a top school. So, either you have to be IQ or you have to have money. These people did not have IQ, of course, they are film stars, how much IQ can they have, And then, but what they had lot of money and they hire what in the US they call it whatever academic counselors they hired, and depending on the amount of money you pay, they will put you in that kind of school. So, this particular student got admitted to UCLA and under the sports quota, and the worst part was this student by mistake boasted about it in the Facebook. That is the disaster, that I never forget about this whatever XYZ game the counselor put that person in. She never played, not only that game, she does not know what that game is, she never played any game in her life. But that counselor faked all the documents, all the forgery. What is the end result? Parents went to jail for few days, but students' admission did not get cancelled. The student still graduated from UCLA. I tracked that Jadavpur student, I tracked that UCLA student, both graduated. So, I think this is a good social engineering. If I need to go to jail for my kid to get a degree from MIT, I would do that. Everybody else will forget. I am pretty sure nobody else knows this story except me. So, if you want your kid to be admitted in MIT, Stanford, IIT Chennai, Mumbai, just figure out one of the way and just be ready to go to jail or bribe few more people and you will be fine. If the social engineering was not supportive, many of those malware will not survive. What is the another social engineering aspect of it? This cryptocurrency. Ransomware will not survive if there is no mechanism of hiding that payment. If somebody transacts money from your bank account, let us say State Bank of India, takes to Axis Bank within India, the Indian government or the agency would be able to find it, detect it, catch the person, put it in jail. What if it goes to a bank in Nigeria? You can't do anything. What if it goes to a cryptocurrency? Nobody knows where it went. But cryptocurrency is not going to go away because lot of rich people invested in it. So, it is a conflict of interest, including all these ministers, big presidents in all these countries. They and their family member invested huge amount of money. They have no vested interest in getting rid of cryptocurrency. Therefore, malware is going to flourish. So, when we complain about malware being bad, we need to ask ourselves as a society, we are creating that social engineering for it to happen. We are creating a society of bribing. We are creating a society where my kid is not intelligent enough, instead of saying, okay, you deserve to be begging on the street, we do not buy them a plate and put them begging on the street, we put them in private engineering colleges. So, if we are paying through the system, then malware will happen, malware will flourish. If everybody stop giving bribes, then bribing system will go away. Everybody wants to take shortcut, that is why it is an attacker's paradise. So, that we basically talked about. Let us zoom into each of them. So, in the malware, if you look at it, what it does, its objective is different. And again, this is a summary of worldwide. So, business average per company, how much they paid. So, business disruption, information loss, revenue loss, equipment damage and all that stuff. So, on an average 70% of the companies were affected by some form of malware, where they have to make some payment in the vicinity of million. Now, of course, people do not report, because if I report my company has malware attack, that basically says I have lousy employees who cannot do information management, or I have lousy employees who can get into this honey trap and all that stuff. I do not want to reveal that information. In fact, there is a prestigious university in India where they hired a high paid professor, higher salary than me in India, which turned out to be a complete fraud. There was a person with that name resume, went to Himalayas and became a saint or got killed, nobody knows. This person took the identity of such a big individual, like somebody took identity of me and getting high paid job in one of the private engineering colleges, and it turned out that person was never penalized. And the reason was this big university with getting all these money from all these sponsors have no vested interest in revealing the fact they made such a blunder. They never pursued it in a court or never posted it to police. So, this person did this audacity, yet got scot free. And how did it happen? Our department chair Sartaj Sahni visited that university, and this director of that institute say, hey, I would introduce you to such a guy, big guy XYZ, and we hired and this and that. My professor's antenna went on, the department chair, and when the department chair met, of course you realize who the hell are you, and then rest of the story is basically it's hush money payment. Nobody, they made a deal, nobody will say anything about it in the public. And this is very interesting phenomena, and this continues. Let us zoom into one of those kind of thing, and before I go there, I kind of tried to look at all these 3000, 4000 known malware we have today. I tried to put it in different categories. Some of them are infectious, like think of viruses, worm. So, if anybody touches it, they just spread, that is the infectious. Some of them has the property of concealment. Again, remember, I categorize them, but some of them may fall into two categories, although I did not put them. So, concealment, basically they will hide. The power of this one is not, their objective is I want to spread and I want to have lot of kids, but rather I want to just go somewhere, hide, so that nobody else can find me. So, there are Trojan horses, logic bomb, rootkits. I will take example and zoom into them. And then some of the malware, the primary objective is to steal something, some information, whether the spyware, keylogger, screen scraper, and then some has objective of making money. So, classical is ransomware. And in fact, some of the dialers, I do not know how phone system works here in US, if you have a postpaid, and then there are certain numbers, if you call, you have to pay like for example $1 per minute. So, mostly those are kind of illegal facility with illegal calls, but basically somebody will call you and you will think, oh, where the call came from, you call and they will just keep chatting nonsense. Basically they will be killing your time, but eventually your phone company will bill you. You call that number, and that number is a paid, not a toll free number. That number you have to pay for every minute you talk, irrespective of you have unlimited call facility, does not matter. For those set of numbers you have to pay. So, similar, those are for profit. Then malware as a platform for other attacks. So, botnet, I will talk about backdoor, trapdoor. So, they are basically some malware they installed there and they are sitting there. That would be a launching pad for other malware. Let us say I am a fraud and you are a fraud. I basically said I already made the fraud scheme and you can use me, but you have to give this % commission. I already have trapdoor there. I will let you use it, but then you have to, whatever money you make, you have to give this much of cut. So, then that is those kind of malware. So, let us start with the one of the simplest one, Guwahati, also known as bash light. So, basically these are used for targeting Linux systems. So, before I go any further, so even 10-15 years ago, people used to feel there is something wrong about Windows operating system and Bill Gates, because all attacks, everything is on Windows operating system, and nobody is talking about Linux or Mac. And I knew even then, I even talked about it in extensively, because there is no benefit for the malware developer to make lot of money, because if you have only small fraction of community using Linux, it is not worth it to waste my time and attack those stuff. So, now the Linux is such a broad user, from Android handheld devices to computers, or Mac also so much use. Now, you have attack for everything, and this is one of the first on the Linux system, that is why I put it in there. So, they basically infiltrate IoT devices, IoT as in, for example, your router in your house, your automated door system, the thermostat, the thermostat or the refrigerator, smart refrigerator and all that stuff, and then they try to do distributed denial of service attack. So, basically they try to get a full foothold using some technology called cell shock and to the vulnerable devices, and they remotely execute command to launch this one. So, the key idea still remains the same, that they have a central kind of server, and then they are trying to check. Think about it, my housing community has 200 houses, right, and some of them the doors will not be closed. So, let us say I am one of the person coming and knocking at the door. While I am knocking at the door, I may try rotating the knob. If I keep doing in every houses, and whichever house I get in, I can just get in and start putting my foothold. Similar analogy, but slightly different. In a house you have lot of IoT devices, it will try reaching and hacking any of them, whichever you get access you get in, and then try to see how do I get foothold on more of them, and then you try kind of keep sending fake messages to create the denial of service attack. PN-scan is another one in Linux Trojan. So, basically ARM, which is the de facto processor for embedded devices, they have majority market share. MIPS, which is the earlier version of we talked about the vector MIPS. So, this is the MIPS. PowerPC, this is the architecture developed jointly by Freescale, IBM, and so IBM kind of owns it. So, for those architecture this infection work, it is basically a software Trojan, which I will zoom in, but the mode of operand for this software Trojan is basically tries the brute force to get the password. Let us say if you have access to my laptop, you keep trying different password, unless there is a mechanism that after the third try it will kind of lock for 16 minutes, it will keep allowing. Of course, if my password is long and all that character, the amount of try you have to do too much, but many times people do not do that. Many times it is 1 2 3 4 5, or it is just your birthday, my birthday, the day you first kissed, or whatever it is, which is much easier to guess. I have to, if I do little bit of research on you, and then basically the space becomes significantly smaller. And once you are able to get a foothold, then that is basically what it is. And most of the attack actually not sophisticated. Let us say if I want to attack one of the investigative agency in India, then all I have to do just compromise one of the person, just being friendly, just walking around and seeing the password, few characters of it while walking, because most people have no ethical values, take it from me. If they are standing, you will be believing when you are typing password, they are supposed to turn their head, they do not. If they find a purse on the street, many people will not take it to the police station, they will just put it in their pocket. How honest you are, you can figure out. Once you find a purse or a diamond on the street, then you will figure out how honest you are. So, given the fact, then if I can compromise just one person, that is pretty much all I need. In the whole, I can take down the whole system. It's that's so basically once I get that person's password, I am a sysadmin in that company, whether it's a CIA or FBI or whatever it is. Then Mirai is another sophisticated one, where it's basically it's collectively lot of the components placed together to mount the basically attack, and this is kind of works if you never change the factory settings of your IoT devices. This Mirai attack actually works very well. Now, I am to talk about software Trojan. The basic idea is they want to hide. How many of you know this story? What is the name of the lady in that story? Yes.
I don't know the overall view, but I do know there's a story that this Roman Empire was time. So the soldiers were inside the horse.
That's the boring part. That's the last page. How many of you know the first page of the story? First of all, this is a mythical story. It's not real, but this is important for our today's discussion. How many of you know the central figure of that story? Not the horse. Helen. Yeah, so apparently she is the most beautiful woman in the world, and she does not exist, but we can still fall in love, right? It's not unethical, right? It's okay. If somebody does not exist, you want to fall in love, it's all right. So, basically the people from Troy, also known as Trojans, they captured Helen from Sparta, and Sparta of course will not give it up, their own princess or queen, I always forget, anyway she does not exist. So, they came to fight, and they figured out the fortress boundary they could not penetrate. So, they basically left everything or whatever including a horse, they gone. When everything is come down, the people from Troy, also known as Trojans, they came out and they saw this horse, and all the so called brilliant people, dumb people, oh this is a consolation prize, they wanted to say sorry, they left it and they pulled it inside their fort, and there were soldiers inside it. In the middle of the night, these soldiers came out, basically killed everybody. I do not know what happened to Helen, last page does not say it, but the key idea here is that you would be your own destroyer. It's like you carrying a money to give your own killer. That's a plot from a movie. So, basically The people from Troy or Trojans are pulling this horse from the enemy and putting in their fortified castle just to be killed by the enemy. That is the idea of Troy. So, the key idea is the enemy soldiers were hidden secretly inside at the stomach of the horse. That is the key idea. So, today I am going to talk about software Trojan, but few days later I am going to talk about hardware Trojan, but that is the how efficiently can I hide, right. So, anytime you go to a hotel room, they give you a free upgrade, do not take it. Anytime you get to a hotel room and the price looks too good to be true, do not take it, because most likely they have camera and they are selling you in the market. Rest I do not want to say what they are selling. So, and so basically in the Trojan horse, in the software, they basically will hide, it is a piece of software, they will do nothing unless whatever the attacker designed it for, whenever they want to activate, that is when they will activate and they will act. Now, when you are doing the traditional software testing, you should not be able to detect it, that is the key idea. You have millions of lines of code, 5, 10, 20, 100 lines of code, some function hidden there. If you run your normal regression test suite, it should not show anything funny at the output, nothing should happen. That is the idea of hiding. When I talk about hardware Trojan, I will get more into detail how can you hide in a broad daylight. So, basically that is expects overt and expected. So, every time it will behave like normal, only when it is needed, then it is going to be attacking, and such kind of people are all around us. They will pretend as a friend as long as you are helping them in their homework and all that stuff, and then they will backstab you when needed, absolutely when it is needed. And this is the kind of example attacker, the kind of functions they do. Then trapdoor or backdoor. So, basically it is a secret entry into a system. So, let us say I am a designer in the company, I am a disgruntled employee, I am unhappy, my promotion did not happen or something, I put a backdoor, right, or somebody paid me to put a backdoor in the system, so that when that system is in use, people can make use of it. Of course, not the good people, bad people can make use it, and it could be also can be included in the compiler. The compiler codes itself, GCC, let us say I have somehow access to GCC, I am one of the developer people who can go and modify it, then that GCC itself will be there. It will not be able to detect. Only time when a person X from a specific country Y compiles a program for a nuclear reactor, I will show an example of that, only then the code will have something malicious embedded in the compiled code. Every other time it is going to do a perfect compilation, because that is not the intention of that backdoor. Logic bomb, as the name suggests, it is a similar functionality, but it would explode only absolutely when needed, and any information I am sharing here, these are public, feel free to share, it is all right. So, and here is the example. So, it is 1918 on, not too long ago, it is a Trans-Siberian pipeline incident. So, a KGB operative was supposed to steal some information, and US CIA got that information, and then there is a farewell dossier, and the company basically inserted a logic bomb. So, basically you wanted to come to my house and steal, I basically stolen it from you, and the thing was, it was a big disaster, so much of fire, whole pipeline getting burst. It was probably the first most explosive thing other than nuclear reactor that can be seen from space. So, it basically backfired. You know what KGB is, right. So, it backfired, KGB wanted to do something, it backfired on the KGB. Spyware, as the name suggests, is basically used for spying. It anytime you are typing a keyboard, and most of you have spyware in your system, most of you. If you are visiting any website which you are not proud to tell your friends or your parents, or you are not proud to show me right now, then most likely you have that software installed. And early days you have to have permission to install. These days all these high tech web browsing plugin and user friendly thing, it basically enabled malware to be installed even if you do not click the link. If you just open the email, that is enough permission for me to get installed in your system. I sent you an email, you open that email, that is big enough. Of course, it would be easier for me to get a deep foothold if you can click the link button or download an attachment and play it. Oh, there is a nice video, it's worth watching and modifying, or some cool stuff I say based on your usage profile, and then you use it and that is it. So, bottom line, how do you save yourself from all of this? Just focus on studies, focus on doing PhD, do not look left, do not look right, then you will be fine. If you do anything else, you are knowingly doing it. Do not tell me later I did not know it, I told you. Scareware, most of the, anytime an email says you have to respond immediately, there is a sense of urgency, or like if you do not do this, something will happen, then this story will happen. When my sister died, we were looking at that room, she was 13, and there was a piece of paper. There was about one religious goddess, and somebody wrote that postcard, 15 paisa postcard, and it was supposed to be sent to 15 or 20 people to scam other people. My mom, till she died, she believed because my sister did not send this postcard to 20 people, that is why she passed away. And that information propagated to everybody, and that is basically the social engineering. I understand sister passing away is an unfortunate event, but I am pretty sure it has nothing to do with not spamming rest of the world, but the scareware is that technique. If you do not forward, somebody will die, something will happen, or you have to act immediately, tax Indian government revenue services, or somebody has a arrest warrant, we can stop all of that if you pay this much by this day through this avenue, all of them are scareware technique. In fact, the most one people fall for, suddenly you are visiting some weird website you are not supposed to visit, or I do not know whether you are. So, then it pops up, oh, ransomware got installed and you have to do this, that is actually fake, no ransomware got installed, you just shut down your system or something, it goes away. It is basically a fake scareware so that you kind of pay money. So, stuff like that will show up, and it is not important what it says. This one I talked about, this is my most favorite one, because many of these vulnerabilities we as researcher know, but this one was classic. This is a major vulnerability, the enemies of United States made use of it, then National Security Agency basically kind of fallen in their own trap, and it got revealed that they actually knew about it. They are using it to spy on US citizens, or at least the US citizen who believe have connection to North Korea, calling somebody in Iran or Russia, what are they talking about. So, that is vulnerability, that is the ransomware, and this is kind of the how skin shows up, that we locked all of your files, all of your directories, and if you do not pay this much $300 by that day through this Bitcoin, then that is pretty much, you will not be able to access any of those. Now, two word of caution, many times this screen is fake, they did not actually do anything, and even if you pay, there is no guarantee you will be able to recover all of your files, that is the fact, take it from me. Even if you pay, you will not be able to recover. Instead, just forget about those things, that is gone, but you and I can do that. Most institutes, companies, hospitals, they can't. When I show you those horror stories, you will see the real life world stories, they actually pay. Sometimes it is not $300, it is in the order of millions, 5, 10, 20, 100, depending on how big. Recent attack was on Los Angeles school district, but they basically attack those, and attacking is very simple. Actually, attacker's life is so easy, you can be extremely rich in no time, and most of the time they actually get paid, most of the time, and nothing happens to them. They have big houses in Bahamas, in Spain and France and Laguna Beach, they have all those nice expensive houses. So, the key idea is of ransomware is basically they do couple of things. So, first of all, through some mechanism you kind of, so they will get a foothold in your laptop, desktop, whatever you are using, they get a foothold of there, they get installed. You clicked on an email, you did something, enter your information, this credit card is too good to be believed, all that stuff. In fact, there are many ATM machines in many countries I have visited, those are all fake ATM machines. You insert your card, they will never let you take it out, you punch the password, they will scan it, and that is pretty much you are done, unless you within few seconds you take this out and or within a day you just block that card, they have everything. Then there are cameras, when you are typing these numbers, they are basically getting your the password you are typing, and about your card you walk through, I walk through with a scanner, I get everything about your card. So, everything I covered from ATM card to your all this stuff, it is all covered, right. So, you can scan and you can get all of those. So, they get a foothold of that, and once they get a foothold, then basically in opportune moment they will block and encrypt all your file. Why am I saying all of this? Can anybody tell me why am I saying it encrypts all the files, that word I am using? Yes.
Encrypts because so that we cannot decrypt it.
So that we can decrypt, that is their advantage. For me, if I know a program sitting there and encrypted too many files, it does not seem like a normal behavior, then that is how ransomware detection works. Because for a detection to work, you have to know the behavior of a malware. For ransomware, behavior is suddenly they will be trying to get foothold of 10, 100, 1000 whatever files or directory they want to encrypt. Too many encrypt operation or functions should be happening in a very short span of time. Any question? So, ransomware, I have few words here, and then ransomware detection. So, when you do ransomware detection or any academic researcher, you are going to see a plot like that. If you do some time specific values, you are noting in this particular case some encryption or sub function of encryption routine. For normal computation, there is not going to be anything, but in other computations it is very high. So, just by looking at this graph, you should be able to think, well, then ransomware detection is easy. How come every system does not come with default ransomware detection? Any of you have any answers for that? If difference is so clear cut, that we should be able to detect and stop any ransomware, why not? For two reasons. One is not just this ransomware detection, any antivirus tool you have in your system, it is based on some kind of what do I call it, some kind of equation. If value, this is a value, if value x is less than equal to 5, then do something. It is basically, we call it a signature. There is a signature for every known malware or spamware, ransomware, any of those known signature. If you let us say you have a anti firewall or antivirus like Symantec, that is the biggest company in the world, then they already have known all the things, they analyzed it, they have the signature, and anytime you install, it is a list of millions of signature. Whenever that antivirus software runs, it is basically anything, any program you start, any process starts in your system, it checks for one of those signature. If it matches, it will stop it, block it, put it in quarantine, move all the data and all that stuff and inform you. The problem with that is the developer of ransomware is also aware of that you are checking x less than equal to 5, whatever the, it could be more complicated, x less than equal to 5 and something or something, it is a big complicated equation. They were aware of it. They will try to basically pretend x is not less than equal to 5, right. So, if the assumption is a thief always wears a jeans, so then I am not going to wear a jeans. When I want to rob a bank, I will wear some dhoti, kurta, whatever makes me look like I am a gentleman, that is what I will wear. If x less than equal to 5 such a problem, okay, I will make sure x is not less than equal to 5. So, for example, percentage of cache misses or number of branch misprediction, if that is a problem, okay, I will not do that, then that solves the problem. So, that is basically one issue. Second issue is I am illustrating here, let me try to erase this. Yes, please.
So does that mean it activates after it has been scanned or?
No, that only means whatever feature you are looking for, the feature or the equation. I used word x, it could be number of instruction less than 500 or branch misprediction more than 20%, whatever it is, me as a ransomware developer will add some fake branches in my program, and I will make sure branch misprediction is greater than, lower than, whatever you are checking. I will just make sure whatever you are checking, I will just misguide that. So that but the thing is, the way it works is a cat and mouse game. Now Symantec get to know about it, there is another ransomware attack, and they have a modified signature. That is when they say please update the antivirus. When they say update or patch, it is nothing but whatever the signature file you have, it will add to that signature file, or it will modify some of the signature. If a new malware comes into the picture, they get to analyze it, another signature would be added to the system. That is what it is. But the second problem that I was talking about, basically when the malware detection should detect, ransomware detection should detect it. If it detects too early, just ransomware started, then the problem is, because ransomware does this registration, get permission, load algorithm, then it start doing encryption. If it if it does too early, then it is because you have limited information and lot of false positive. It may be normal program, you might be just encrypting your own file, maybe disk backup, whatever it is, you are encrypting on your own, and it could be misconstrued as ransomware. If you do little late, okay, let me see little bit more time, by that time system already encrypted all of them, it is too late. Even if you detected, oh, I found a ransomware, so what, they already encrypted your files. So, because different types of malware have different characteristics, even if you know how to detect it, detection becomes a problem. So, it is not that people are not aware of it, people are aware of it, but it becomes a problem. Let us talk about virus. So, as the name virus says, it is basically spreads, right. So, there are basically self replicating code, and then operates when infected, if spread condition, then for target file, if not infected, alter the virus. So, it is basically the program that kind of self propagates and makes copies. In one router it got access, another router is connected, it make a copy and transfer there, because once you are in a trusted zone or inside my house, let us say a lot of things, but the assumption is all the routers and thermostat, TV, door, security automation, everybody talks to each other, they are all trustworthy. If you infected one of them, then you have the liberty to infect everybody else, because now you are trusted within the system. Worm, basically self replicating malware that does not require a host program, it propagates fully working itself to other machines. So, basically probing, exploitation, replication, payload, whatever it wants to do. Then Morris worm is one of the most popular, actually the first version of the worm, the source code is also available. Zombie and botnet. So, these are actually backdoor, these are actually backdoor. So, you have some code, or think about it, you introduced a vulnerability in the system for other people to exploit it later. That botnet is a program that will sit there, it would kind of help other malware to act. Rootkit is similar, I am going to skip rootkit, and there are so many types of rootkits also. So, botnet, rootkit, all of those have the same property. They basically, so the reason botnet and rootkit are separated, rootkit as the name suggests, it has a word root, that means it is pretty much like they will be a botnet for sysadmin kind of people, they have root access, they get to install on the sysadmin space, and botnets are like normal user space, you and I. So, think about in IIT sysadmin who those people are. So, then basically in their computer how to get installed, what to do, what utilities, how to change. So, those are known as rootkits. And installed I have basically talked about, and I will show basically real world examples, so that you kind of know. I am going to skip all of them, how do they get accept. Now, I am going to talk about famous malware attack. Now, this is not a laundry list, these are my favorites, there are many more, but some of the key ideas I talked about, including social engineering, that was used in the fullest extent in each of them. So, I will start with the colonial pipeline attack, and I basically got affected by it. So, I have first hand experience. So, there is every country you need a pipeline to supply the fuel, right, how much can you carry by trucks and all that. So, there is a pipeline from all the way from Florida to all the way from New Jersey and all that stuff. on the boundary. So, this is owned by a company called Colonial, and this pipeline attack basically before I talk about that pipe, first of all I want you to understand there is a pipeline through these states which basically supply the fuel. And I want you to understand that in United States, I did not get such a data for India or public data. In United States, so when you have a pipeline systems, there are known vulnerabilities. It is known to community, good people like us, it is also known to the attacker, right. So, there and that I forgot. In security domain, it's the common understanding is everybody knows everything. Security domain assumption is not I will not tell you what security algorithm I am using in my system, whether it is AES, ECC, I will talk about those cryptographic algorithms, that is whole day dedicated for that. Assumption is everybody knows everything except the key. Can you still attack it? Then if you can attack it, then my security system is not a good system. So, that is why you might be wondering why US government made it public, because vulnerability or anything about it, that information should be available to everybody. So, in the act of sabotage, somebody goes and breaks the pipeline. That was the recent pipeline breakage below the ocean, the Russian pipeline that happened, but that is not what I am talking about. Then cyber attack, this is the attack I am going to zoom in. Colonial pipeline attack actually happened in the distribution system of the cyber on the business system. There is also physical attack, you can just make explosion by putting fire in the pump, you can control and sorry my apology, the control system was attacked in this pipeline. So, what actually happened, it is a long story, may not be readable, but the key idea is hacker basically company or group named DarkSide. There is a group called DarkSide, and they basically got access to this network, Colonial pipeline network, and then lot of data they basically stole within certain time and so on and so forth. Then they demanded 75 Bitcoin at that time, which was about 4.4 million at that point, and then that whole supply got disrupted. Basically think about it, fuel is not flowing. Now, if fuel is not flowing, there was still some fuel, whatever fuel was there, but what happened the moment I realized there is no fuel, what am I going to do next thing? I will not only fill my car, I will fill bunch of drums also in my house. That panic buying and all of that caused huge disaster. Hospitals do not have fuel, the people in the home, in US many people before they die, they actually in home they have all these services, they do not die in hospitals, they live up to 90, 95, 100, and those houses do not have fuel, and the old people either they do not have kids or the kids do not care about their parents, or parents do not want kid to be bothered about, they are pretty much all alone, they can't go and buy fuel. So, it became a total chaos in so many states in the USA, there is no fuel, and in fact the trucks which will carry fuel, that those trucks also have no fuel, and most of it caused by the price has gone up drastically, and most of it is caused by people actually panic buying. If people are like, okay, now there is a fuel shortage, let me not drive, people did not do that, and every gas station there is fighting, hustling like third world country, people are punching, shouting at each other, big line, and everybody is trying to cut in, bang, scratch, it is unbelievable unless you see for 1 or 2 weeks from May 6 to June 8 or almost a month, it is just unbelievable pain. So, that damage or that loss is huge, lot more than 4.4 million, that is huge. Let us talk about Stuxnet malware. So, this malware is basically, so United States has an objective for Iran to stop doing nuclear enrichment, to build nuclear power or nuclear bomb or whatever it is. They tried lot of stuff, putting what is this called economic, all that sanctions and all that stuff, deal and all that stuff, nothing worked. While none of these are working, US tried something very interesting. For that to work, so there is a malware called Stuxnet, later we figured that out, and the person who figured out is a 14-year-old kid who figured out all of that. Before all of that happened, still nobody knew about it. So, Stuxnet basically it works with the Siemens control software, I do not know whether it is written anywhere, Siemens control software. So, it basically any industrial automation systems, most industrial automation systems uses Siemens control systems, and this Stuxnet basically once it gets a full foothold on Siemens control system, it can control the whole thing. And what basically it did or wanted to do, the centrifuge, the speed it rotates, if you change the speed even little bit, then uranium enrichment time increases by another 40 years. So, that is what it pushed. So, their enrichment was, let us say in 2 to 3 years they are supposed to get bomb quality uranium material, it got pushed by another 40 to 50 years. And how did that go to such a highly protected uranium facility? The way it works, social engineering. US did a study that if you throw USB stick on the street, how many people pick it up, how many people pick it up, take it to their home, how many people pick it up, take it to their office, how many people actually insert that in their office. They had all the data. Based on that, they figured out just throwing USB sticks in Iran or vicinity of the area will work. Of course, they tried to infiltrate, that did not work, lot of US agents got killed. So, then they basically had to adopt for this social experiment. They threw all these USB sticks with Stuxnet, and one of the one of those dudes basically picked up that USB stick and put it on the system to copy file to do legitimate stuff. Stuxnet got installed, and that basically delayed the uranium enrichment. That is why still US, Iran negotiate. One president comes in and says, I want to make a deal with you, do not do the enrichment, allow international visitors to see that you are not doing it. Then Trump comes in and says, I do not give a shit, I am not going to deal with you. So, all that pros and cons goes on, but that is the Stuxnet. The interesting part is one 14-year-old kid actually figured it out, and they basically broken it that this code, what is it trying to do, Siemens control, who cares, who created it, and basically then it worked. Then the third example, which is also my favorite example, and in the security community anytime I teach, this is the first thing I teach. When you want to mount an attack, if you are an attacker, as a researcher we have to wear 2 caps, one is blue cap as a defender, one is red cap as a attacker. So, when you are an attacker, your objective should be other person should have no clue. So, most of the examples in this world I have shown, even in the if you go and look at the common weaknesses, common vulnerabilities database, most of the attacks are based on 5 or 6 well known weaknesses. But this is an example I want to show you where you talk about a weakness nobody even knew about, that did not even exist. So, United States, every country do it. I always take example of United States because I am sure what I am saying, and it's perfectly fine. Other country I know examples, I am not, that is why Israel pager attack I did not talk about, I know the intricate details of it. So, there is a Cold War time 1960s, 62, 64. So, US wanted to know everything about Russia at that time. Now, of course, Russia is not going to give you that information. Even in Cold War time there was a consulate, Russian consulate in Washington DC. US is not able to infiltrate to that consulate. They tried all kind of techniques, it did not work. So, then US basically one day they got a news, they are buying a copier machine, and that is it. Xerox is a US based company, and it is a Xerox copier 914. This is an exact picture, not at that consulate, that 914 model I found it, and that is basically a copier similar to this bought. And what happened, even the moment US got that news, they had very short time, like few months or a year, they hired somebody called Ray Zuputh, and this person's job was, can you in the actual design of this, can you fit a camera there? So, you have to fit a camera, so that anything they photocopy you should be able to take picture, and it took them lot of time to perfect it, and that is the copier they sent to the Russian consulate. And the idea of this is it will keep on taking images until the buffer become full. When buffer become full, the software will basically say I am not working, there is a problem in the system. Repairman gets called, and this guy is the repairman. Ray would go in, download, take the buffer, reset the system, system starts working, comes out. So, basically two things US had to do, three things: knowing that Russian embassy is going to install a copier. Second thing is, those days there were de facto only one company, Xerox. It is not that they did not have a choice. These days they might have gone for some other companies, but then second thing they had to do, they had to perfect that photocopy, buffering and all that mechanism. And third thing they had to do is that the repairman has to be a US spy. So, that basically all three worked, and that is basically the story. And antivirus I briefly talk about. So, I mostly talked about the attack, but antivirus is actually a very useful industry. There are many companies, and so the Symantec, and there are many firewall, many of those stuff, but as I summarized, it relies on the premise that I know the characteristics of the malware. Therefore, I know the signature of it. Therefore, any program executing in my system, within few milliseconds I will be able to figure out whether it's any of the known signature matches with the program, then I will block it, stop it, quarantine it, move it to a directory where it can't do any more damages, and that kind of stuff. And in the, that's pretty much what brings me to the conclusion. So, malware is a serious threat to computing systems, and you should not view it as a simple piece of software. It comes with a huge amount of social engineering. We need to be greedy, otherwise we will not install it, right. So, it plays on human emotion, society emotion. Many of the example malware I have shown, at least the popular one, that is a state level attack. A country wants to invest all of their money to attack another country. And by the way, in the previous example I did not give you data because that is not public. This Xerox machine or that attack US applied on how many embassies of their enemy country, including their friend country. So, because I am getting recorded, I did not want to give you that information. You will not find that information. And then there are a lot of software based solutions, which is basically it matches some signature, and I talked about that can be bypassed by program behaving or changing its behavior. If I know what signature you are checking for me, then I will change my signature, so that you can't detect me. Then there are some hardware based solution, and in the next lecture I will talk about how we can use explainable AI to kind of detect some of these malwares, not all of them. Thank you.
Thank you, sir. So, we will have a 30 minutes break now. We will again come back at 4. We have tea outside, so you can have help yourself.
যদি ঠিক কপি না করেছো তাড়াতাড়ি ফিনিশ করো, যদি ঠিক কপি না করেছো তাড়াতাড়ি নিচে যাও একটু। হ্যাঁ ঠিক আছে, ঠিক কপি করেছো। সারপ্রাইজিংলি গলা আজ ঠিক আছে, কালকে বোধহয় ফার্স্টে বলে এটা একটুখানি ভীষণ ড্যামেজ হয়ে গেছিল।
এতে কোয়ান্টাম কম্পিউটার 4 ঘন্টা 5 ঘন্টা করে বলছিল, কোয়ান্টাম কম্পিউটার অবশ্য 2 দিন চলে গেল।
তার চেয়ে খারাপ ছিল প্রথম যখন জ্বর নিয়ে আসে 6 ঘন্টা 7 ঘন্টা হয় কন্টিনিউয়াস,
সেটা তো
ব্যাড আইডিয়া।
এই 4 ঘন্টাটা কেন স্টুডেন্টের জন্য ঠিক আছে, আমাদের জন্য একটু টাইম, আমি 4 ঘন্টা বলিনি, আর 2 ঘন্টা। Start or something?
Good afternoon. We are going to talk about today about malware detection. In the previous lecture we looked at different types of malware and how they get installed and why it's difficult to find or detect them, and we briefly talked about some of the existing techniques. I am going to talk about few more techniques and zoom into this malware detection aspect. So, this lecture would be beneficial if you are trying to work in the malware detection area. So, here is a kind of a brief recap of what exists today. So, basically most of the solutions, or at least the commercial solutions, are software based solution. That basically means for all of those software based solutions the key idea is the following. So, the key idea of the following for any of the solution any of the solution also known as antivirus, any of the antivirus solution that is installed in your computer, they basically scan your system on a regular basis if you keep the scan enabled, right. And the things that they scan, that depends on the basically the signature file. So, you have a signature file, you have a signature file in the system, and that signature file you can think of equation like x greater than equal to 5, number of instruction less than something, and so on and so forth, and each of the entry corresponds to one malware. This could be malware 1, this could be malware 2, and this could be malware 3, and they have thousands of such entries they have. Now, you have to understand antivirus is also a software program. That software program is running, you have to keep it enabled, and that software program is running on your platform in your computer. So, this is your core 1 processor, core 1, this is your core 2, right. And typically antivirus software in a normal system is supposed to run on the security enclave. If you remember the Intel SGX or TDX or AMD ACV, and we have a dedicated dev to talk about this trusted execution environment in the security enclave, or if the security enclave does not exist, then in the super user mode this antivirus software would be running here, and everything else, your normal application like your browser is running here, all other applications running here. The job of this antivirus software while running here to monitor what other programs are running in other cores, and while they are running what is their footprint, what are they doing, and does any of them match with any of my signatures. So, that is why if you kind of if you use a Linux environment and in the command line you do a top, you are going to see a n number of processes running, and you might be wondering, wait a minute, only thing I did, and the one on the top would be top, which you just started. You might be thinking I am not running all of them, many of them are system related, including the antivirus software which is running for monitoring all other software, which is checking the signature and then trying to figure out the program that is currently running, is it a malware or is it a benign program. Any questions? The problem with this idea is the developer of this malware is aware of this signature file. So, whichever company software you are using for, so let us say Symantec, or that is one of the most used one, there are many other companies, whichever company software you are using is completely known to the attacker, what is their signature file, how many malware. In fact, this information is publicly available, signatures for different known malware. So, that is why in the malware community there is a concept of known knowns, known knowns, known unknowns, and unknown unknowns. So, known knowns is basically obvious, it is just you know. What do you think is known unknown? What does that mean about any malware? What do you think it may mean, known unknown?
It could mean that I know that there is something existing, but I don't know exactly what it is.
Could be, but in this case known unknown mean I know the malware, but the part that is unknown or I know the malware or malware type, let us say it is a botnet, but what I am unknown about, how many of the botnets are attacking me. It is a denial of distributed denial of service attack, but how many of them are attacking, I do not know that. So, it is a known adversary, but what you do not know. So, you have a friend, you know this person is going to stab you, but you just do not know how they are going to stab you. Unknown unknown is basically I do not know what software, what malware it is, and I do not know what it is going to do. And this is also known as 0-day malware. It is a new malware that just came in, that is also known as, let me write it out, 0-day malware. 0-day meaning that is the first day anybody ever heard about it. Of course, once it become known, Symantec analyzes, Symantec will find an entry for it, signature, and then they will do the update of your antivirus. In fact, it turned out I found out the hardest possible malware to fix would be when your antivirus software is getting installed or updating, you interrupt it. Then it did not finish itself, it will not kill itself, and it can't correct itself. Just try doing it, you have to throw that computer or you have to reinstall everything, and you can create that funny thing. But anyway, so the problem of this known unknown, known known, any of those, that this malware actually knows this stuff, whatever things you are checking they will change itself. That basically known as malware with obfuscation or metamorphic abilities. Obfuscation, as I explained, if the idea is a thief normally wears a jeans, then I do not want to wear a jeans, I will wear dhoti or pajama or whatever it is that is treated as a normal human being. So, then basically that would be like obfuscation. I am obfuscate myself as a gentleman, I obfuscate myself as somebody does not match with any of these signature. Metamorphic is because when I install myself in your computer, Symantec will know about it, they will update it, I have to change myself while I am inside your system, I will change myself. So, while I am wearing a dhoti, I am also carrying a pajama in my backpack. The moment you put dhoti also in here, I will just change that and then I will start wearing pajama. If pajama also gets into that thing, I will need to pick out something from my backpack so that I can move forward. So, this is basically what I meant by can be bypassed by obfuscation or metamorphic features. So, then there are solutions people are talking about. I am going to zoom into one of these solutions with this whole lecture, so that you kind of see deep dive into how people work. So, hardware based solution, what is the key idea? So, what was the problem in this space anyway? The problem was, so one of the exact equation for a malware was percentage of branch predictions or branch misprediction. Let us say percentage of branch misprediction, that is one of the exact equation in the signature file. If as a developer of an or an attacker of a malware, if I know branches of misprediction, you are looking for less than equal to 0.2 or 20%, then I want to add a lot of branches in my code and I will let it mispredict, and those are fake branches, they have no effect to the functionality, because as a malware I want to do some functionality. Remember, ransomware tries to encrypt the code, those branches have no meaning. Simply there are some branches if I greater than 5 and all that stuff, and you know that I will not be 5, and similar branches you can add, and the way processor deals with them, they start using it. When it get mispredicted, they will convert into no operation. So, that is where hardware based solutions become useful, because the instruction that getting killed as no operation, hardware knows about it. So, it is not going to count those branches that was mispredicted and was not never used. So, then it will only count the one that were used, right. So, that basically means if I take the example of human, we should be asking them to get rid of their clothes. That would be analogous to hardware based solution. We get to the rock bottom of the instruction that actually gets executed. The way we solve that is using something called, I mean there are many ways, I am going to talk about only 3 in today's lecture. One is hardware performance counter, second one is embedded trace buffer, and third one is electromagnetic emanation. These two are of course functional, and this is basically side channel. I intentionally chose those basically those 3, so that you kind of get an idea, and I want to tell you the whole big picture of the story of, and this story applies to any hardware based solution, and there are hundreds and hundreds of paper, although I cited one of my own, there are hundreds of paper in this area. So, the key idea is I want to have a malware detection mechanism installed in my computer, and as I told you, if you do not do it right, your malware detection mechanism itself would be one of the biggest malware if you ever encountered, if you do not do it right. So, malware detection mechanism is supposed to sit in your computer, and then it is supposed to continuously monitor what else is running in your computer device, whatever it is, and what needs to decide in layman terms, is it running any of the malware or is it running benign normal program. It needs to distinguish between normal and abnormal, right. And how does it do that? I basically tries to summarize by looking at all the papers that are out there. It is basically I need to look some of the hardware features. What features, depending on, are you doing malware detection based on functionality, or are you doing based on side channel. So, depending on that you choose one of those, then you need to choose basically different types of what type of evasive malware, ransomware, botnet you are trying to detect, which one are you targeting. Third one is what solution you are using. For example, are you using explainable AI, are you using real time acceleration. Remember we talked about the GPU, TPU, FPGA based acceleration, what type of evasive attack you are accessing. So, that is basically the story. What is the end result? Either it says a malware detected and let me quarantine it, or it says it is a benign program. Of course, here I am saying as if you are running only one program, of course, you are running many programs. Any questions on this big flow, where this program sits and run to what is your final outcome, either it is malware or it is not a malware. and this is basically classification type machine learning in this particular example. So, let us talk about hardware performance counter based malware detection. So, first thing I want to talk about is that how many of you know about hardware performance counter? So, any processor you buy, anything in your computer, whether it is a ARM processor, whether it is a Intel processor, whether it is an AMD processor, MIPS processor, RISC-V processor, it does not matter what processor, even tiny microcontroller. So, like Motorola, Siemens and all those microcontroller in your devices, all of them comes with something called performance counter. What does counter counts? Different architectural events. So, I can list some of those events for you. So, for example, number of instructions executed. Now, you can control some of those based on the variables, number of instructions so far, total, number of instruction per millisecond, you can control that, but number of instruction. Then it would also give you, let us say, number of cache accesses, how many load instructions are sent to the cache, number or percentage of misses, how many cache misses are there, number of branches, how many branches are there, or what percentage of instructions are branches, how many of them are mispredicted. So, pretty much any architectural event you can think of, there is a counter for it. There is about 300 or 400 counter give and take, and most of this work when we talk about, people use normally top 10 or 15. The way you want to think about, now start putting the machine learning cap on your head. Each of these performance counter is nothing but a feature for machine learning tool. So, really machine learning very quickly need to figure out that out of rank them out top 5 or 10, and let us just focus on those, monitor those, build a model with those. When it builds a model, what it is really doing, you know, it is building that equation. Then you might be saying, wait a minute, if it is building that equation, number of instructions greater than this, something less than that, how is it different from what Symantec had on software based solution we talked about? Let me ask that question again. We have all these hardware performance counter, these are potential input for the machine learning model. Think of neural network. I am going to train the neural network based on those. I am going to tell them, by the way, this program you are running, this is malware, by the way, this is one you are running. So, then internally it is going to build an equation or a curve or a model that is basically going to say, well, if the number of instructions is greater than 1000 and percentage of misses less than something, it is kind of creates kind of a complex, it kind of creates a complex equations like that internally as a model during training time. Then during prediction time, if you run a program, it is basically going to match with that equation. If it matches, it is malware, if it does not match, it is benign. My question is, it seems exactly the same. Symantec sends a set of equations to you, we call them signature, and machine learning model builds a signature. Then what is the difference? Why am I even trying to suggest, give a hypothesis, hardware based solution is more accurate? Why? What is the catch? Catch is the Symantec signature is static, malware signature is dynamic. You look at the behavior, look at the portfolio of the program, then you train and build. Now, you could argue, wait a minute, now malware knows that is how the machine learning model is built, it can do metamorphic changes, then you have to train again the machine learning model. Still it is a dynamic signature, you can change it, you can retrain it. But the key idea is hardware performance counter, as the name suggests, is counter, it counts. Machine learning model makes use of it, and I will show some of the usage. So, first thing we have to choose the input for the machine learning model, that is basically the counter, and I listed some of them, number of instruction, exception, change of context, bus access. And then thing is, you have to train the machine learning model, use the overall statistics is vulnerable, sophisticated, and the most of the time people focus on this aspect of time sequential information. What does that mean? That means if you just use performance counter, let us say number of instruction, that is probably not going to help, or number percentage of misses. If you say percentage of misses between time A and time B, that difference if you look, that is more useful. That is the meaning of time sequential data. You have data at different time point, that is the sequential nature, that is the time sequential method. And if you want to do that, then recurrent neural network is going to be ideal fit for this kind of context, or you ignore all about this and you use large language model, then you do not have to know anything or learn anything. Yes, please.
Right now we talked about that.
Turn it on, please. Okay, I will repeat your question, you go ahead.
So right now we talked that the signature gets copied by the attacker, and that's why they are able to metamorphose and other stuff. So if the
No, signature is not copied by the attacker. Signature, we have to assume signature know, I mean attacker knows what signature is used, somehow they know,
so if
because rest of the world knows, everybody knows.
so if an ML builds that equation of some certain features or a combination of those, is it not easy, like the attacker won't be able to easily decrypt that equation from the ML and then like metamorphose just to get that change the signature.
So, the question is that it may be difficult for the attacker to know the equation inside machine learning model. Answer is yes and no. I think answer is yes from the perspective machine learning, if it is making a decision yes or no, it is not an explainable AI, nobody knows, forget about the attacker, nobody knows what the hell is going on. But the answer is no from the perspective that when you build any security objective or a lock, you can't assume, oh well, attacker or thief does not know the which day I am in my house and which day I am not. You have to assume attacker knows everything about it, still can you defend, that is the idea, right. So, even as close as 100 years ago, there used to be a dacoit called Devi Chaudharani, and she used to send letters to the houses that I am going to come on that day to steal your and rob your house, and she was successful every time. So, that is how, if you are an attacker, that is how you should be doing, and if you are a defender, you should be telling every rest of the world, this is how I am defending, I am pretty sure you will not be able to attack. That is the spirit in the security world. Everything should be known to everybody except the key. Now, moving target defense is one of the solution people use against metamorphic malware. It is very expensive. So, the idea is that I do not use one machine learning model, I use multiple. The way you as an attacker keep changing yourself, me as a defender, I will keep changing my classifier. How I do, what do, I use a random number generator. Then even if attacker knows you use a classifier, a single one, they might be able to do something. When they know I use multiple, if I am selecting them randomly, unless it is 2 or 3, it is almost impossible, theoretically impossible for the attacker to basically correctly predict which one you are using when. Assumption is the number of classifiers would be large enough, but the problem with this is practically you have to have that many trained model stored in your computer. It is going to slow down the detection, and as we discussed during ransomware detection, if it slows it down, then it basically by that time attack is over, game over. If I am dead, what will the bodyguard do? It is over, right. So, that is all, that is basically about hardware performance based. Next one I want to talk about the embedded trace buffer based. How many of you know what is embedded trace buffer? So, embedded trace buffer is one of the legitimate debugging technique in any design you have access to, not just processor, even network, router, anything. So, the key idea is when you have a design, there is a tiny buffer, although I am not drawing it that tiny, that would allow you to trace certain signals or variables for certain number of clock cycle. ARM allows you to do software control it, many architecture will not allow you to software control, like processors, that is hardware control, meaning during design time which signals would be traced for how many clock cycle. This is typically in the order of 128 signals, this is in the order of 1024 clock cycle. It is a very small number of signal, 128 out of millions or billions of signal would be traced and stored. There is a trade off, I will come to that in a moment. Yes, please. Do you have a phone there? No. Turn on the phone. Yes, now it is on. I can see the red light.
Sir, yes, in the previous slide you mentioned that we will be keep changing the seed, right? Each and every time the attacker knows that what I am using, right? So is it feasible, because the cost will be more and we will be spending more on the hardware part. So
right. So feasibility, that is a different problem.
Yeah.
Does that solve the problem? Yes. So as an academic exercise, publishing paper, it's perfectly fine. Whether any company will adopt it or implement it, that's a different story.
Okay.
So practically there are constraints, as I talked about.
Yeah.
Right. So embedded trace buffer is basically a legitimate structure that's in the design. Most people don't know about it, they don't care about it, only people care about the people who want to debug after the design is fabricated. For you to understand, you have to think about this. If you have million line of code you have written, right? Now debugging million line of code is a problem. All of you want to go to industry, make money, you don't want to do PhD with any of us, that's all right. But the thing you will quickly realize, as soon as you go, you are cleaning somebody else's piece of shit, not documented properly, it is all hacked code, bunch of morons wrote it, and if you want to modify the code, your boss will say go and become a professor. We do not do that, do whatever we asked you to do. Millions of lines of code written by people, nobody knows, they left the company and you have to fix it or fix bunch of bugs within certain day, depending on the severity of that bug. Now yet if you want all those millions of variable, you can do printf. I know printf and it running for millions of clock cycle, that data would be in terabytes, you won't be able to dump or load. Now think of hardware, any integrated, tiny integrated circuit has billions of transistors and you do not have any printf facility. Anything goes wrong, your boss says go and find and fix it. Hardware can't be fixed, that is why firmware patching is done, as I talked in the first day. So what do? Do you ask for blessings from God? That is not going to solve the problem, I can assure you, that is not going to solve the problem. That is why one basically intermediate solution is allowing little bit of space, this is very tiny space, 128 or 256 multiplied by 1024 bits, allowing that. But then there is a lot of associated problem I will not talk about, is it which 128, which 256, that is not going to give you 100% visibility, but which of the signals if you trace you get maximum visibility. If you think of an AND gate, if you trace the output and output at that point happens to be 1, you know these two dude and you can continue that stuff, but if this output is 0, you do not know what are the inputs, right. But either way, that is the key idea and there is lot of research, how do you select trace signal, whatever, but for this discussion what is relevant is that is known as embedded trace buffer, a tiny buffer that is only solely used for debug purposes. Now remember, this debug is not necessarily during design time, this debug could be during design time, mostly during deployment. Anything goes wrong, then customer says oh my god, this happened, that happened, you do not want to spread Disney magic wand, you want to just stop the execution, dump the trace data and from that try to make sense out of it and pray and all that stuff you do. That is the embedded trace buffer. Now how do embedded trace buffer we are going to use? So that data also you can use for your malware detection. Lot of people talk about using cache data, register data, but the problem of that is how quickly the malware detection software can download that registered data. The amount of time it takes to download the cache or registered data, that might be long enough for attack to be successful by then. Any questions on what is embedded trace buffer? It is a tiny debug infrastructure that is useful for debugging. Think of, in lieu of printf, that is all you have in an integrated circuit that is already fabricated, right. There are also concept called scan chain in the design, I did not talk about here, but scan chain basically all the sequential element you have. Remember, any design is sequential element and combinational logic. All the sequential element you have, they are scanned, connected in a chain. Of course, sequential logic connect. So, this is kind of a multiplexer here. So, scan chain idea came from the point of view, again that structure got inserted by different set of people, manufacturing testing people. The reason they inserted, when they want to test a chip for manufacturing defect and they need to pump values to these flip flops to initialize to a known state. And if you have millions of flip flop, initializing that to a known state will take forever, not a minute, not hour, it will take days to do one valid testing, because you cannot test a device without initializing it to a known state. You can't wake me up and ask me interesting question. I am like who, what, where, when. So, I need to be initialized and reset. So, that idea scan chain was invented, so that you keep pumping data whatever values, it goes through a chain. If you have a million flip flop, then you know it will take million clock cycle, that is a lot, but that is still guaranteed. If you do not do that, if you want something to pump and then the sequential logic combinational logic computes, it produces something and then depth of 5, 10, 20 or 100, that is going to take forever, non-deterministic amount of time to initialize all the flip flop. Lot of attacker makes use of this scan chain also, but this time we are only talking about how as a defender you want to use it. How do they take advantage of scan chain? Anybody can tell me? We talked on the day of assertion based validation. So, in the scan mode, when you are doing scan, the time this is used and time this is used, they are totally different. This is typically used after it is manufactured. Let us say chip is manufactured, you built a robot, that robot is used in the Amazon facility to kind of carry the stuff to the truck or wherever, and something went wrong. People would stop that robot, download this data and test. This is used when an integrated circuit that got manufactured even before putting onto the robot, that integrated circuit, are there any manufacturing defects, such as let us say you are drawing two lines, did one of the line, it was supposed to go like this parallel, did it touch one another, this is called bridging fault. Or maybe you are drawing a line, did it got kind of disconnected. Remember, these are all nanometer level. So, here in the order of millimeter, micron would be 1000 times smaller, nano would be another 1000 times smaller, million times thinner than a hair, million times thinner than a hair. That is what those lines are. Some of them might have been disconnected. How do I test it? I put a 1 here and I see if I get a 1 here. To do that, I have to initialize the whole all these flip flops, then I put a 1 and then I check for 1. So, wire by wire, for each of those millions of wire I have to test. Unless you are going to a company to do manufacturing testing, you will never learn about it, but attackers know about it. You as a defender need to know how do they do attack. So, this is used during only manufacturing testing time. How would attacker make use of it? Normal execution going on. Remember, in normal execution the key which is used for encryption and decryption will travel through the system, and there would be a point when key would be completely out in the open right here, which is right in the scan chain. That 128 bit key or 256 bit key would be right in the scan chain. If an attacker can stop execution right then and there and change to manufacturing mode, change the setting of the chip to manufacturing mode, they will be able to dump it from that scan chain.
So, it is like a leakage test.
It is not a leakage, it is basically can you detect when that computation is going, that is a legitimate time when that value is supposed to be there, because key is used for encryption and decryption. If encryption is going on, key should be there. You can't say, oh, I am hiding the key, I will not. If you have a door with a lock, you have to take out the key to open the lock. If your thief is standing right behind you, when you open the lock, thief will get in the house with you, that you can't control. So, that is why in around 2010, 2015, the idea was, the solution was, well, once this manufacturing testing is done and the chip is placed on the robot, this would be sealed. So, that we will not be able to have a mechanism to push anything in from the scan chain and push anything out. Then people found a problem with that, then it's a lot of solutions and in between, but these are the structure that can be used for malware detection. So, let me now get into, instead of zooming in, let me kind of zoom out and talk about how do I go about it. Previously I talked about hardware performance counter, that gives a global perspective, how many instructions. Embedded trace buffer or even scan chain gives you local perspective, right. So, analogy would be, let us say you are looking for the best PhD student or your best spouse possible in the world, and somebody gave you a feedback, yeah, he or she was in my village, kind of a good student. That is a global perspective. Local perspective is you go to that school or where he or she studies or teaches, and you see for a day. Of course, that is one day story, that is one snapshot, one picture. So, one picture versus a movie, which is a picture running in every 20 millisecond frame. So, hardware performance counter gives you an average or a statistics about an event, about a person. This one gives a snapshot of a 1 day, 1 minute, 1 second, whichever you look at it. If you can combine them right, then malware detection would be ideal. So, that is basically what it tries to do, and machine learning model makes use of it. And trace buffer, this is what I talked about, this is the full story. When you design something, of course you verify, but after you manufacture and all that, you have scan chain, which I did not show it here, you also have a trace buffer, and during debug you need, actually not necessarily during deployment, even before you do the deployment, when you want to put your the processor, operating system, compiled code, and you are trying to test it, we call it post silicon validation. At that time also this trace buffer is extremely useful. So, when you run machine learning model, then the first thing you want to talk about, how is it doing in terms of different parameters, right. You are trying to choose different kind of stuff. So, here I am showing you different exploration experiment. So, true positive and false positive, as the name suggests, if during detection it detected a so positive in this example would be benign program. If it detected somebody as benign, it is truly benign, or it is detected somebody as benign, it is actually a malware, it made a mistake. And this diagram is showing, if you increase the ETB width, embedded trace buffer width, basically more signals you are tracing per clock cycle, then your true positive goes up, and of course, naturally your false positive will go down. That is one issue, that is expected. If you have more data, more information, if you have too much more, then machine learning would have another problem, overfitting problem. One more thing it also establishes, we looked at different neural network. First day I talked about normal neural network, I talked about decision tree, I did not talk about random forest. Think of a lot of decision tree together, which is a forest, lot of trees in a forest, lot of decision trees together solving a problem. And if you are trying to figure out which one we choose, it turned out that which one is this normal neural network is actually not that great, but all others are kind of hand to hand, and I am still trying to figure out this brown one or red one. So, this neural network, that KNN, that is basically kind of tends to be doing a little better than rest of them. So, basically that is how you kind of decide which neural network model to use, you decide how much of data, what size of design I can use, sometimes you do not have a choice. This particular one makes assumption you have a control of telling the processor designer what size of ETB embedded trace buffer they should put in. Most of the time you do not have that choice, you have to stay with whatever design it came with. Yes, please. The switch is not on. Yes, please. Oh, it still become off. Maybe keep it on, hold it, it will become red.
Sir, when we're talking about the problems with machine learning models, there is either false positive or false negative. There are two categories of problems. One is like intrusion detection or malware detection, where false negative is very serious than false positive. Suppose we are detecting a suspicious user in a system, and if our system show it is false negative, that means it can lead to a large data breach for any organization. And if it is identified as true false positive, then it will be go for further investigation, even it is a normal access. But false negative is here serious issue. And when we go with the other category of problems like behavior analysis, where false positive is more serious. Suppose a system shows that this kind of person have serious psychological problems, even it has not. So how explainable AI can help us to address these two categories of problems, where we have need false negative address mainly, and some other category of problem where we have to address mainly false positives.
Right. So first short answer is explainable AI cannot help in the exact question you asked. So false negative is of course dangerous, because a malware you allowed it to continue, but when you talk about false positive, even that is not that great, it is not that serious, because if a program is executing some health monitoring system or something and you kind of identify it as a malware, system will shut it off. Think about it, you are running experiments for last 10 days and your paper submission deadline is tomorrow, so and system shuts it off as a malware, I do not think you will be happy. It may not be as serious as somebody encrypting and asking you for money, ransomware, that attack. So for killing a legitimate program thinking it is a malware is not a great idea either. Now going back to explainable AI inherently has the ability to give you some internal information. What you want to do with it, that is kind of different, and I will have some example on the microarchitectural attack days to show you how explainability can help you reduce this false positive, false negative, but it still reduces that by allowing you to train it better by knowing what is going on, not by any magical the nature of explainability. Yes, please.
So you mentioned that the scan chain or the trace buffer is not accessible during functional mode, right? So in the sense when it is installed,
when computation is in progress.
So then how this kind of AI technique will work? The scan chain you won't be able to access, right?
Right. So yeah, but very interesting observation. So the question is, if you have this scan chain or trace, so first of all trace buffer you could be able to use, but scan chain was kind of not allowed during normal execution. Then the question is, if scan chain is not allowed during normal execution and if program is running, how would your malware detector make use of any of the scan chain data? So again, remember, malware detection is working in the super user mode. So as a super user you might have certain privileges to do certain things. For a normal outsider we should not be allowed, and one of the way malware work, they elevates themselves to the super user mode and then they get access to some of these data. So there are those examples, but in this particular case when the malware detection we are doing or all the academic exercises, they are basically stopping the execution, dumping the trace buffer and analyzing them and saying if we could have detected it instead of in lifetime. In fact, for hardware performance counter also same argument applies. Hardware performance counters are nothing but some functions. If you call them too many times, you are interrupting the speed of normal execution of other functions. And hardware performance counter you also have to access in super user mode. You cannot just access, you cannot just get in the command line and ask for tell me how many instructions, you cannot do that. So because of that it introduces overhead. So that is why even when you do any research you probably have to instrument your code with hardware performance, basic block, all that. It is going to significantly slow down the execution of your malware detection algorithm. And if that slowdown is too much, that is not a good solution.
So, in general, how do you access the trace buffer? When I have no idea.
So in general trace buffer is dumped through the debug port in general. Now the question is, once you kind of in ARM processor for example, this is not like hard coded like this, which is all the signals are hard coded completely wired to this and only connection is through the debug port. So internally you can choose which variable you want to trace and internally registers can read and write through that. So in that kind of software controlled trace buffer you will be able to download those values.
It's something that when I run my program,
you can run your program.
I told that you only track my XYZ variable, right? So then they will map those XYZ variable to those registers.
Some of the input ports of this trace buffer and then you will overwrite after every 1024 clock cycle. So you will be able to software programmable trace buffers you will be able to control. Hardware programmable you have to dump, you have to stop execution and that kind of stuff. So that is not like real time malware detection.
So modern processor may not be supporting that, but earlier days they used to have just JTAG cable. So small board they provide JTAG cable for doing programming and to debug the code.
So this is the JTAG port, the one is coming out, this is called JTAG port. So you will be able to dump the data
but
through
nowadays modern system they don't provide this thing, but earlier days they used to provide.
So many of the modern system disabled it for security reasons, but they still provide. JTAG is a international standard.
Yeah.
They have to provide some mechanism. Otherwise, anybody can buy anybody processor build system. Then there would be no way of chaining them together. Like bus specification, JTAG also interface port. So now, of course, if you do just HPC hardware performance counter or ETB, the kind of false positive it kind of creates depending on which architecture, it basically ETB tends to do well in most of the cases, false positive are less. Now I want to move from functional malware detection or machine learning algorithm using functional values as input, whether ETB, HPC, to electromagnetic side channel. So there are days when is it tomorrow? So Dr. Karfa will talk about side channel, but today I just want to give little bit of start just to connect the dot for malware detection. So the electromagnetic emanation, let me talk about what is EM stands for, electromagnetic emanation. So this is an electrical property. Of course we did not talk about power side channel attack, and in layman terms, if you are computing certain functionality and if your device is connected to the power supply, and if I can kind of connect my ammeter or whatever to the power supply where you are drawing power, if I know how much power you are drawing, from that I can figure out what you are computing. That is the basic idea of power side channel attack. And electromagnetic emanation also relies on the same principle. It is just that when there is an electrical activity going on, whether it is consuming power or dissipating power, it dissipates these creates that magnetic field, as the name suggests, electromagnetic field. And if you have a probe you are holding, this is a probe. Typically probes look, if you are holding a manual probe, it will have a handle and then there is a loop around it. That loop will be able to detect. But today, these days, if you are buying high end probes, those probes are very microscopic probe and they move in every millimeter across the surface and they collect the electromagnetic emanation. So capturing electromagnetic emanation itself is an art, because even you are trying to, on an FPGA you are trying to capture, the problem is FPGA where those tower are, or tower microscopic towers are, you have to hold your, first of all you have to know where your logic is and which power supply in that FPGA. If the power supply is here, then for this particular block or set of blocks you have to hold the probe right here. If you hold anywhere else, you are not going to get the footprint, that one. Then you have to understand there are other stuff going on for controlling FPGA, controlling communication, other stuff going on. They will also contribute to this probe, that noise. So, that noise is very significant. So, unlike power side channel analysis, which is very robust, if I can know how much power you are drawing, electromagnetic emanation is lot more difficult to get reason, because if you do not do it right, what you are going to see bunch of noises, even when you are computing, even when not computing. Noise is so much more than the actual computation. Everything will look like a band of, let me, this oscilloscope they are not showing, everything will look like a band of, so this is the band that you are seeing, everything will look like a band of ups and downs, there is no clear demarcation. That is why there is a notion of amplification, hiding noise, subtraction, differential power analysis and all that, but that is the idea of electromagnetic emanation. Now, this is also widely used for malware detection, it is very successful. So, people are able to show that using electromagnetic emanation you can identify how many for loops are there in the program, and if you know the program, which for loop started now. So, that you can do almost 99.99% accuracy. You can figure out what is going on right now using without touching, and the good idea of EM is it is non-intrusive. For power supply based attack, either you have to allow me to connect to your power supply, or your device should have some kind of transistor you should allow me to embed in your design, so that I can measure the power consumption across that one. That is intrusive. Why would you as a normal user allow me to insert a transistor in your printed circuit board or in your computer for me to do these measurements, but whatever it is, that is still intrusive, and you sometimes it may not be applicable, but EM you can always apply, but EM has its own downside. So, if you are starting side channel kind of analysis research, you want to start EM at the end, you want to start with power based side channel analysis, and then you probably want to do delay based side channel analysis. Once you are successful, then you probably want to go for EM based side channel analysis. But whatever you do, because of the availability of EM signal, then EM would go to like oscilloscope, you get that, then you feed it to wherever you want to feed it, then it goes to machine learning model, then machine learning will figure out whether a malware running or not. And how does it figure out? It is the same philosophy. The philosophy of if you recall that in the power side channel analysis, when we talk about, by looking at these waveforms, we can say, well, this is where add operation is going on, this is no operation is going on, and this is where let us say multiplication or square root is going on, because we kind of know how much each of those instruction computes. And in fact, many cases we will be able to figure out because some of the cryptographic day I will talk it more, elliptic curve cryptography, which is one of the most powerful cryptographic algorithm before this post quantum cryptography came in. It has a silly computation inside. If the ith bit of the key is 1, then do something, else do something. This loop has more instruction than this loop. If somebody is observing power variation and you are seeing it goes up, then little, then it goes up and then little, then you know this one is 1, this one is 0, this one is 1, this one is 1, this is 0. You exactly figure out what the key is. But the thing is, you have to identify in that whole story of the oscilloscope where that key processing started. Once you identify those boundaries exactly, then you can exactly find out what is the key through kind of power side channel attack. Same thing you can do through EM. EM is like kind of less reliable. You have to do lot more processing, you have to run lot more traces, you have to do lot of trial and error and elimination, much harder, but you are going to get to the same thing. So, since I am talking about this, anybody knows what is the solution for this? What is the solution people use today? It is called masking. Only reason I am able to figure this out, because this is imbalance. If statement has more instruction, else statement has less instruction. I will put bunch of garbage instruction just to match with this one, so that the power profile becomes exactly the same. But the problem of that is you are unnecessarily introducing power consumption. Instead of going power efficient solution, you are going power inefficient solution, right. So, that is basically EM based malware detection. Now, there are a lot of research effort, and I do not believe some of them are published, some ideas that you could publish as a paper, that can we combine hardware performance counter and EM based solution. How do you do? I have 2-3 ideas I just jotted down. So, hardware performance computer kind of do well with certain things. If certain things is benign, then it is likely to hold. If certain things seems malicious, it needs deeper inspection, and remember this gives a global view, and like embedded trace buffer, EM gives a local view, more detailed view. Think about it, zoomed in. So, this one is giving you a lot of trace. Out of the trace, HPC is zoomed you into the tiny part of the trace. Now, you zoom into that trace to the EM based detection, then that is saying it is benign or it is malicious. So, for when you have programs with interrupts, story works slightly differently. Certain programs has a lot of interrupts, then HPC will be able to do normal execution, and or if there is an interrupt, you do interrupt handling, and then on a normal execution you can do EM based detection. Some other thing, if it is a ETB traces can aid EM based detection. So, for example, there are control intensive programs, then you can start with EM based detection, and if it is a control operation, then you go with embedded. If it is a data centric operation, then it is a ETB. What is control centric? If you have too many for loops, too many if statements. What is data intensive? Think about all the multimedia code and GPU, lot of data processing, not too many control flow. Then this kind of method would be a better combination of EM and HPC. Some people have tried other different ways depending on the thing, depending on what access you have. So, for example, so there is a whole day dedicated for network on chip. So, this is what one of the network I am showing, or on chip network, where you are kind of have some network where the traffic is going on. The only sad part is the traffic inside the network is essentially unencrypted, because doing encryption and at that speed and that lightweight is kind of a problem. But whatever it is, if the attacker or defender is able to download that data or whatever is going on, then you can mount kind of different type of attack or different type of defense. And many time, if any of you have access to any of the new AMD machines, you might be able to download this. For many others, there is no direct access to any of the network on chip network, any of the dumping ability. Now, the way, if you want to evaluate any of those, if you want to start experiment, one of the board that kind of going to work for you is Zinc SOC evaluation board, and this is one of the most popular board. One of the reason that is the case, because this board pretty much has everything you need, different types of port, and you have the FPGA in there, you have the processor in there, you pretty much have everything in there. So, you can program them, and this particular one, the k nearest neighbor and all that, some of the experiments you have already seen, and these experiments I am going to show you, PN-scan, Basslight, Mirai, those experiment, and in the benign benchmark netstat and ping. One of the reasons these benign benchmarks we chose, because these are also used by PN-scan for sure, some of them Basslight and Mirai also. So, when ping or netstat runs by themselves versus they are called by some malware program, can you differentiate them? That is basically the complexity. And again I am showing some data on HPC and ETB, the actual data does not matter, who does better. If you have access to network on chip, depending on the so this percentage is basically injection rate. What rate of injection your data is, then there is a different kind of portfolio between false positive and false negative story. Now, for all of these malware, this slide I have shown earlier, for all of these ETB based or hardware performance counter based malware detection, some of the models people used, I showed it earlier, I want to zoom in. So, data format that typically is useful is basically, I call it register. Sometimes getting register values are difficult. It could be some ETB values, it could be hardware performance counter values. So, wherever may be, these are the sources and these are the clock cycle, certain values, whatever those values are, that is the data that you need to provide to the machine learning during training. That is the input. Then typically, because it is a time sequential data, typically recurrent neural network, and specifically there is a name for it, long short term memory, LSTM, that is actually perfect fit for this kind of malware detection data, and most of the paper use some variation of recurrent neural network and long short term memory. I have seen most of the papers they use long short term memory LSTM model, and this particular for malware detection case, people is more successful using gradient descent to kind of quickly converge on a decision that whether it is a malware or whether it is a benign. You can use other ones, and if you can show better than the existing papers, then that could be a good paper by itself. And this particular one I talked about. So, once you have all these information from explainability AI perspective, the way it helps, you get certain values associated to certain clock signal or certain variable. Then whichever has the highest weight, then you kind of know that so think of this one as the weight of that polynomial. So, that weight is higher, that basically means something happened in clock cycle 4. So, here is some kind of some results to show you the detection accuracy of bash-like malware using different kind of random forest, decision tree, and all that different kind of models. And in this particular example, explainable AI models are doing better. Of course, the whole story I am not talking about that how much iterations it took and how much effort it needed for explainable AI versus others, and you would expect the similar analogy for PN scan and as well as the Mirai example. One other thing that is also important, we talked briefly, it is not just the accuracy, can you detect the malware, are you detecting some of the benign program as malware, that is the false positive rate. That is why anytime you do research or publish anything, in addition to showing those 3 diagram analyzing, you have to present how many of the cases you are catching it as a wrong answer. So, you are catching a benign program as a, and you want to make sure your solution is better and in terms of false positive rate than the state of the art or whatever you are comparing with. I believe that brings me to the conclusion. So, malware is a serious threat to computing system, and we talked about different software based solution like antivirus software AVS, and they can be bypassed. I basically talked about how do you use some of the hardware primitives like hardware performance counter, trace buffer to kind of solve those problems, and I kind of show certain types of result where it could help you in good malware detection. So, if you have any question, I will be happy to take, otherwise have a wonderful day.
Okay, so we are done for the day. Just one final announcement is that Friday is holy as we discussed. So, Friday is become Sunday now. We have all the lecture planned for Friday will be on same schedule on Sunday grades. So, please note that and plan your so we can plan accordingly, right? Plan your schedule, we can that. Okay, thank you. So, we will meet again tomorrow at 10 p.m.